Audio, video, okay? Please reply. Okay. Okay. Good morning, good morning, good morning, all of you. Okay, so today is second inning of chemistry and topics which I am going to deal with, you are knowing. So we have to discuss so many topics, so without wasting time, I am starting first topic there. Basic concepts, some basic principles and techniques for the organic chemistry. Okay, so let's start with this problem. Which bond is more polar in the following pair of molecule? What is given there? First is given CH3H and CH3Br. So carbon, hydrogen, carbon, bromine. Where EN difference more? Obviously in case of carbon, bromine, EN difference is more. And you are knowing if delta EN is more, polarity in the bond. Polarity in bond is more. So based on this we can say in first case out of CH3H and CH3Br, obviously CH3Br is more polar. Likewise, second case CH3NH2 and CH3OH given. So carbon nitrogen bond, carbon oxygen bond. EN difference more in case of carbon oxygen. Since EN difference more in case of carbon oxygen, obviously carbon oxygen bond is more polar. Third one is given CH3OH and CH3SH. So carbon oxygen, carbon sulfur. Delta En is more for carbon oxygen, so carbon oxygen bond is more polar. Concept is very simple. If delta En value is more, polarity is more. Next problem. In which carbon-carbon bond for this molecule the inductive effect is expected to be the least? You are knowing inductive effect is a distance dependent effect. Inductive effect is distance dependent. So for example, if I am taking this given compound, normal propyl bromide, if this compound taken, so in this case this bromine is minus I group will attract electron density towards itself. What will happen? This will develop delta positive charge on this carbon. Next delta positive will be smaller than first delta positive. This is represented by small delta plus, and this next delta plus is smaller than the previous one, means it is represented by triple delta plus. So if I characterize these things, I can say delta plus is bigger than double delta plus and double delta plus bigger than triple delta plus. So inductive effect is a distance dependent. Okay. First carbon, hydrogen, carbon, bromine. They are asking polarity of the bond. So carbon, bromine, EN difference is more than carbon, hydrogen. Okay. Okay. Now listen. In this case, what will happen? You are knowing inductive effect is distance dependent. Distance dependent means as you increase the distance, inductive effect is going to decrease. So obviously maximum inductive effect observed for first carbon attached to bromine and minimum for this. So for this bond I can say inductive effect is least, or for this carbon inductive effect is least. Reason is very simple. You can observe delta plus bigger than double delta plus, double delta bigger than triple delta plus. Concept is very simple. Inductive effect is distance dependent effect. Next question. Write the resonance structure of CH3CO minus and so the movement of electron. CH3CO minus means acetate ion, CH3C double bond O minus. You are knowing this minus will give electron like this and pi bond will break. So its next RS will be what? CH3C O minus double bond O. These are the two RS of CH3CO minus. Okay. Now in this case, these are the two RS for CH3CO minus. Both are identical. Both are identical. Both are identical. They are called equivalent RS. Because of this, let's say this bond is given X and this bond is given Y. Bond length X will be equal to Y. Okay, so how many RS are coming there? Two RS are coming. Both are identical. Both are equivalent. That is why in this case I can say both related bond lengths for the resonance X and Y, they are equal. Next one. Write the resonance structure of CH3. Okay, these three RS are given to you and you have to find the contribution and stability. So if you want to find the stability of RS, for the stability of RS, rule is very simple. First you have to go for the octet. Second you have to go for formal charge. Second, you have to go for formal charge. Third, you have to go for EN and size. And fourth, you have to go for charge separation. Okay. Octet complete is more stable than incomplete octet. First factor. Formal charge means what? If more formal charge is present. More formal charge present means more number of atoms are carrying charges. Then stability will be less. So if complete octet more stable. Formal charge more, stability less. Formal charge more, stability less. So we can say in general, if formal charge is more, stability is going to be less. Then EN and size. EN is important in case of period and size is important in the case of group. EN is important in case of same atom also, and charge is separation. Okay, so now in this case, how I will check? First of all, I will go for the octet. First case, all atoms have complete octet. Second case, this carbocation is having 6 electrons, the valence shell, it has incomplete octet. Incomplete octet. Come to the third case. In this third case, this O plus, you can count also oxygen. How many electrons the valence shell of oxygen atom? Oxygen atom, how many electrons in the valence shell? 6 electrons. 6 electron plus 1 charge should become 5, and single bond, so 6. It has only 6 electrons in the valence shell, means it is also having incomplete octet. So based on this, I can say structure 1 is more stable than 2 and 3. Then next factor is what? Formal charge. So look at formal charge. This carbon has plus, this oxygen has minus, this oxygen has plus, this carbon has minus. Means 2 atoms are carrying charge. Here also 2 atoms are carrying charge. Formal charge factor become same. The next factor, EN and size. Carbon, oxygen belong to same EN, same period. So we have to check by the EN. What we can say in this case? Oxygen, more EN contains minus charge, and you are knowing minus charge is more stable on more EN. Minus charge is more stable on more EN. So based on this is minus on more EN. Obviously this is more stable than third. So second is more stable than third. This is the order of stability. So order of contribution will be just this is more stable, so its contribution will be more. Any RS who is more stable will contribute more in the resonance hybrid. In this case, contribution of third is least, and it is a 0 also as per the NCERT. There is no contribution. Okay, next question. Okay, next one. Explain why CH3C is more stable than CH3, CH2 and CH3 plus. Okay, so you can check there. If I am writing this first carbocation, it is given CH3, CH3, CH3 plus. Next carbocation CH3, CH2 plus, and next one is a CH3 plus. Now in this case, concept is very simple. For this carbocation, this is directly attached carbon, and this is having how many H here? This is 3H, this is 3H, this is also 3H. Means this carbocation stabilized by 3, 9 alpha H, hyperconjugation effect of 9 alpha H. This carbocation stabilized by hyperconjugation effect of 3 alpha H, and this is not having any stabilization effect. So first is having stabilized on 9 alpha H, second is having 3 alpha H. So obviously first is more stable than second, and second is more stable than last. This is the stability order. Concept is very simple. More number of alpha H, more hyperconjugation, more stable. Okay, one more point in this case. If examiner asks how this carbon is stabilized, so you can say it is stabilized by hyperconjugation effect of 9 alpha H and plus I effect of these 3 CH3 groups. Okay, next question. So hyperconjugation effect is observed in case of carbocation, carbon theoretical and unsaturated system. Unsaturated system means alkene, alkyne and aromatic compound like benzene, alkyl benzene. In these cases we can get hyperconjugation effect. Alkyl benzene means if alpha hydrogen is attached to the is present in alkyl benzene, then it can go for hyperconjugation effect. Next, methods of purification. Sublimation, only one point is enough. Sublimation is valid if out of impurity and organic compound is sublime in nature. So only one important point is there, that the technique is based on the above principle known as, okay. Okay, sublimation is known as sublimation and used to separate sublime compound from non-sublime impurity. Only one line is very important here. This is used to separate sublime compound from non-sublime impurities. Okay, crystallization. For crystallization, only one important point. For crystallization, only one important point. Ki solubility is more at high temperature. Solubility is more at high temperature and solubility is low at room temperature. Then you can go for crystallization method. One concept is enough for crystallization. If solubility is more at high temperature and low at room temperature, then crystallization method can be applied. Okay, next one, distillation. Distillation means in this case simple distillation. If boiling point difference is large, let's say A and B are present and they have large difference of boiling point, then you can go for distillation method. Important example, aniline and chloroform mixture is separated by distillation. Aniline, chloroform. In this case, very important example for the distillation. This one, the vapors, okay. Chloroform and aniline are easily separated by the technique of simple distillation, or obviously in this case simple distillation. This example is a very important. So two important points: distillation valid if difference of boiling point is significantly large, and second point, chloroform aniline mixture is separated by the technique of distillation. Okay, this is one important point for this question. Next one, fractional distillation. Two important points. First, fractional distillation we are applying when difference of boiling point is less. Then we are going for this method. And second method, different fractions of crude oil separated by this method. Fractions of crude oil are separated by this method, fractional distillation. Okay, so fractions in this case, two important points. If difference is less, then fractional distillation. And second point, key fractions of crude oil in petroleum industry are separated by fractional distillation. This line is a very important. For fractional distillation, one more term is important, theoretical plate. This term is also very important. Theoretical plate is providing surface for the heat exchange. Only one line you have to know. Theoretical plate provides surface for heat exchange. Okay. Distillation under reduced pressure. Two conditions are there. If boiling point of organic compound is very high, or organic compound decompose at or below boiling point, then we are going for distillation under reduced pressure. Two conditions are there for the distillation under reduced pressure. One condition, boiling point of organic compound is very high, or organic compound is going to decompose at or below its boiling point. If these two conditions are there, then we are going for distillation under reduced pressure. Example, glycerol can be separated from spent lye in soap industry by this method. Okay or not? So this concept very easy but very important. In what condition we are going for distillation under reduced pressure? One condition, boiling point of organic compound very high, or second condition, organic compound is going to decompose at or below its boiling point. Example, glycerol. Next one is steam distillation. It is condition is a very important for this. Steam distillation is applied if organic compound is steam volatile but immiscible in water. Steam volatile and immiscible in water. This line is very important. Steam volatile and immiscible with water. If this condition followed, then steam distillation can be applied. If organic compound is steam volatile and immiscible in water, then this method can be applied. Example is very important. Two important examples are there. One is aniline water mixture, and second orthonitrophenol orthonitrophenol and paranitrophenol. Orthonitrophenol and paranitrophenol. Out of ortho and paranitrophenol, orthonitrophenol is a steam volatile. Orthonitrophenol is a steam volatile. So very important point, steam distillation applicable if organic compound is steam volatile and immiscible in water or immiscible with water. And example, aniline water mixture, aniline water mixture is separated by this method, and mixture of ortho and paranitrophenol is also separated by this method. Out of ortho paranitrophenol, orthonitrophenol is a steam volatile. This is very important. Aromatic oils are also separated by this method. Aromatic oils are also separated by this method. Okay. Next one, differential extraction. Differential extraction. In this technique only one important point, key, organic compound is more soluble in organic solvent and less in water. This is the concept for this differential extraction. Chromatography, 3-4 important terms are there. In this case, most important is this retardation factor. Retardation factor is a distance traveled by substance from baseline upon distance traveled by solvent from the baseline. We have two type of chromatography: adsorption chromatography and partition chromatography. Adsorption chromatography and partition chromatography. Adsorption chromatography, two important examples as per our syllabus: thin layer chromatography and column chromatography. Partition chromatography, one example, paper chromatography. Paper chromatography, very easy to memorize. Partition chromatography, P for partition, P for paper. Adsorption chromatography, two important examples, thin layer chromatography and column chromatography. And retardation factor formula is very important: distance traveled by compound from the baseline upon distance traveled by the solvent from baseline. This is called retardation factor in chromatography. Okay, next we have to go for the quantitative estimation of organic compounds. Qualitative analysis of organic compound. Qualitative analysis is discussed in detail in salt analysis part, so you can revise from there. So I will not focus on this much, okay, because it is already discussed in salt analysis part. Okay, so why to waste time for this? Okay, quantitative analysis. Quantitative analysis. Okay, so quantitative analysis part is discussed in salt analysis part, so I will not stress much about this. So let's focus on the quantitative analysis. Quantitative analysis, estimation of carbon and hydrogen. In this case, what we are doing, organic compound taken. This organic compound is going to be heated with oxygen in the presence of cupric oxide, CuO. What will happen? Carbon dioxide gas will release and hydrogen will come out. This carbon dioxide is absorbed by KOS solution, and water is absorbed by anhydrous CaCl2. Then this very simple, mass gain by KOH solution is equal to mass of carbon dioxide and mass gain by the CaCl2 solution. Mass gain by anhydrous CaCl2 part is equal to the mass of water. By this we can easily estimate percentage of carbon and hydrogen in organic compound. We'll discuss through the numerical. Next, the estimation of nitrogen. We have two methods. One is the Dumas method and another is Kjeldahl's method. Dumas Dumas method, very important point, it is based on nitrogen gas evolved. It is based on nitrogen gas evolved. In this case, 2-3 important points are there. In Dumas method, what we are doing? In Dumas method, what we are doing? We are performing reaction in the environment of carbon dioxide. We are performing we are performing reaction in the environment of carbon dioxide. What we are doing? Organic compound taken, let's say CXHY NZ. This is heated with CuO. So what will happen when we are heating with CuO? What will happen? Oxygen bind with carbon, convert this into carbon dioxide. This oxygen bind with hydrogen, convert this into water. And this nitrogen is a free as N2. Some nitrogen atoms are converted into nitrogen oxide, let's say NaOY. Some nitrogen elements are converted into oxide, let's say NaOB. This is converted into nitrogen by giving copper. So concept is very simple. Dumas method is based on nitrogen. What we are doing? We are heating with cupric oxide and getting nitrogen. And this nitrogen is collected over, this is a KOH solution, and nitrogen gas is collected here. Here nitrogen gas is collected over KOH solution. Nitrogen gas is collected over KOH solution. Okay, this is about the Dumas method. Okay, let's solve the problem. In Dumas method, it is given in Dumas method for the estimation of nitrogen, 0.3 gram of an organic compound give 50 ml of nitrogen. 50 ml of nitrogen. For Dumas method, very simple method is there. You have to apply formula PV upon T. PV upon T once for the given condition and one for the NTP condition. You have to apply formula P1 V1 T1 is equal to P2 V2 T2. P2 V2 T2. This you have to apply, one for the given condition and one for the NTP condition. For example, let's observe here. In Dumas method, for the estimation of nitrogen, 0.3 gram of organic compound is giving 50 ml of nitrogen. 50 ml of nitrogen. So now in this case I can say nitrogen is how much? In the place of volume of this I can write 50 ml of nitrogen. Nitrogen collected at 300 Kelvin temperature. So this temperature is 300 Kelvin. Okay, you have to write temperature in Kelvin. Now this point is very important. And 715 pressure. So this 715 pressure is a total pressure. Total pressure is 715. And here it is written aqueous tension is a 15. Means out of 715, 15 pressure is because of water vapor. So P total is equal to, in this case I can say P nitrogen plus aqueous tension. Aqueous tension is equal to 715. Aqueous tension given 15. So nitrogen pressure is coming 700. So this pressure for nitrogen is 700. This is given condition. Other side we have to write pressure, NTP pressure, which is 760 millimeter of Hg. Volume we have to find at NTP. For the nitrogen gas, volume we have to find at NTP for the nitrogen gas, and temperature is a 273.15. I'm writing only 273. Now from this we can calculate volume of nitrogen. From this we can calculate volume of nitrogen. How much volume will come? You can easily solve this. This is gone. This is also gone. So it is a 7 into 5 into 273. Divide by 3, divide by 76. This is the volume of nitrogen. Then how to calculate moles of nitrogen? Very easy. This is volume of nitrogen. Now I want to find moles of nitrogen. I will solve there only. Volume of nitrogen. This is coming in ml. Sir, why ml? Because given in ml na. So divided by 22,400. This is this is moles of nitrogen. Then mass of nitrogen N2 multiplied by 28. Multiplied by 28. This is mass. Why 28? Because it is N2. And percentage of nitrogen divided by mass of organic compound multiplied by 100. Simple method. This is a very easy question. In this case, only one point is important, that total pressure minus aqueous tension is the pressure of nitrogen. Okay. Next is Kjeldahl's method. Kjeldahl's method. In this case, one thing is very important. Ki what is taken in Kjeldahl's flask? Answer: organic compound plus copper sulfate plus concentrated sulfuric acid, and here copper sulfate is acting as catalyst. Another point, Kjeldahl's method not valid for azo compounds. Azo compounds not valid for nitro compounds, and not valid for those compounds who are having nitrogen in the ring. Let's solve the problem. During the estimation of nitrogen present in an organic compound by Kjeldahl's method, ammonia evolved from 0.5 gram of the compound in Kjeldahl's estimation neutralize 10 ml of 1 molar sulfuric acid. For Kjeldahl's method problem, just focus on the data and apply normal mole and mole analysis, which you are knowing. What is given there? 10 ml of 1 molar sulfuric acid. 10 ml 1 molar means what? It is a 10 millimole of sulfuric acid. By molarity into volume is giving millimole volume in ml. So this is 10 millimole of sulfuric acid. It is reacted with what? Ammonia gas. Ammonia, Kjeldahl's method is based on NH3. So just write the balanced reaction NH3 plus H2SO4. So 2NH3 plus H2SO4 is equal to product or ammonium sulfate. Okay, ammonium sulfate, NH4 whole thrice SO4. How many millimoles of sulfuric acid taken? 10 millimole of sulfuric acid taken. 10 millimole of sulfuric acid are actually reacting with the ammonia. So 1 sulfuric acid means 2 ammonia. So 10 means NH3 is 20 millimoles. 20 millimoles of NH3 means what? Mass 1 NH3 contains 1 nitrogen. So simply we can find mass of nitrogen 20 into 10 power minus 3 into, it is N. So I will multiply it by 14. This is mass of nitrogen. Mass of nitrogen upon mass of organic compound 0.5 multiplied by 100 is the percentage of nitrogen. Very simple method. Okay. Carius method is based on the precipitation. Let's solve problems. What is given there? In Carius method of the estimation of halogen, 0.15 gram of an organic compound gave 0.12 grams of AgBr. Focus on the data. 0.12 grams of AgBr. So moles of AgBr is equal to mass given 0.12 divided by its molar mass. Molar mass is 188. This is what moles of AgBr. Now you can observe from the formula that 1 AgBr contains 1 bromine. So this many moles will contain same number of bromine atom. Bromines, what I can say? Moles of bromine is equal to 0.12 upon 188. This is the exactly moles of bromine. So what is the mass of bromine multiplied by its molar mass into means 80. This is mass of bromine. So percentage of bromine will be equal to what? This is mass of bromine divided by mass of organic compound 0.15 multiplied by 100. This is what? Percentage of bromine. Okay. Next question. Organic compound estimated 0.157 gram of an organic compound gave 0.4813 grams of barium sulfate. What is it? Again, same thing I will say. Focus on the data. What is given to you? 0.4813 grams of barium sulfate. So what will be the moles of barium sulfate? Mass given 0.4813 and its molar mass is 233. Moles is equal to mass upon molar mass. This is the moles of barium sulfate. Now what we can observe from the formula? 1 barium sulfate contain 1 sulfur na bhai. So obviously moles of sulfur is also same because 1 barium sulfate contains 1 sulfur. This is moles of sulfur. So what will be the mass of sulfur? Mass of sulfur multiplied by the molar mass of sulfur, that is 32. So what is the percentage of sulfur? Percentage of sulfur divided by the mass of organic compound given 0.157 multiplied by 100. This is the percentage of sulfur. Very easy question. Don't be scared of these concepts. They are simply based on mole analysis. They are simply based on mole analysis. Okay. For the estimation of phosphorus, you have to focus on two compounds, NH4 thrice PO4 12MO3 yellow precipitate and Mg2P2O7. These two compounds are very important for the estimation of phosphorus. You have to emphasize on these two compounds for the estimation of phosphorus. For the estimation of oxygen, you have to emphasize on one compound I2O5. Examiner may ask which reagent is used for the estimation of oxygen. Answer is I2O5. Very important. Which reagent is used for the estimation of oxygen as well as carbon monoxide also? Answer is I2O5. Emphasize on this I2O5. Emphasize on this I2O5. Okay. And one last and very important technique, that is called CHN elemental analyzer. CHN elemental analyzer, which can estimate percentage, or which can give result, which can display the result on the screen. It is one device which is giving percentage of carbon, hydrogen and nitrogen in organic compound by taking very small amount of sample, that is 1 to 3 milligram. That is 1 to 3 milligram. Very important concept. Examiner may ask which technique can be used to find the percentage of carbon, hydrogen, nitrogen by using very small quantity of sample in very less time. Answer is CHN elemental analyzer. So if I emphasize, for nitrogen we have three methods. One is Dumas method, second Kjeldahl's method, and one technique is used, that is CHN elemental analyzer. CHN, name itself suggesting it is used for carbon, hydrogen and nitrogen. It is used for carbon, hydrogen and nitrogen. So okay, this is done. So let's focus on the next chapter, that is hydrocarbon. Hydrocarbon. Hydrocarbons means organic compound which is consisting of only carbon and hydrogen. Like alkene, alkene, alkyne and aromatic hydrocarbons like benzene, toluene, etc. Now, problem number 13.1. Write the structures of different chain isomers of alkane corresponding to the formula C6H14. Write the structures of different isomers of alkane corresponding to the molecular formula C6H14. C6H14. If you observe this formula, this is matching with the formula of alkane CnH2n plus 2, means there is no pi bond. It is matching with the alkane formula, and means there is no pi bond. Now you can easily solve. How many carbons are given? 6 carbon. So first possibility, I can make 6 carbon chain. Next possibility, I can make 5 carbon chain. If I am making 5 carbon chain, 1 carbon is extra. Na? 1 carbon is extra. For that 1 extra carbon, I have 2 possibilities. One possibility I can connect to this carbon, and next possibility I can connect to this carbon. If someone is saying, sir, why you are not connecting to this carbon? Are nalayak, if you are connecting to this carbon, it is same na yaar. 1, 2, 3, 4, 5, 6 carbon. 1, 2, 3, 4, 5, 6 carbon. 1, 2, 3, 4, 5, 6 carbon. So if you are connected to this terminal carbon, it is same as the previous 6 carbon chain na yaar. Don't say, sir, this is straight chain, this is hanging chain. Are nalayak, both are same. Is it clear or not? So now concept is very simple. If you want to find the isomers, what is given there? C6H14 matching with the alkane formula, no pi bond, 6 carbons. First possibility, 6 carbon chain. What next possibility is 5 carbon chain. Now in 5 carbon chain, how many for 5 carbon chain? 1 carbon extra. Now my total carbon count is 6. 1 carbon extra. 1 carbon is extra. For that extra carbon, I have 2 possibilities. I can connect at number 2 and I can connect to number 3. Don't say to connect at this carbon. If you are connecting this carbon, it is previous one. 6 carbon chain, 5 carbon chain. Then next what? 4 carbon chain. 4 carbon chain. 1, 2, 3, 4 carbon chain. How many carbons are extra? How many carbons are extra? 2 carbons are extra. One possibility, I can connect both carbons like this, and second possibility, I can connect both carbons like this. Is it clear or not? Is it clear or not? So what we can observe, how many chain isomers are coming for this? 1, 2, 3, 4, 5. Very important question. Very important question. Okay, they are the chain isomers or structural isomers of C6H14. Next one, write the structures of different isomeric alkyl alcohols corresponding to the molecular formula C5. Okay, now given C5H12O given, or I can simply write C5H11OH. This is given. For this you have to find number of alcohols, number of structural alcohols. What is the method? Very simple. Focus on the carbon skeleton. What is given there? If it is given C5H12O, write as C5H11OH. And if they are asking about the alcohols, so I will think only about the alcohols, not about the ethers. Now what is given there? C5H11 means one possibility 5 carbon chain, next possibility 4 carbon chain, and next possibility 3 carbon chain. Very simple concept here. What is given here? What is given to you? What is given to C5 na? First possibility 5 carbon chain, next possibility 4 carbon chain, next possibility 3 carbon chain. Now in this chain, what we have to connect? OH. What we have to connect? OH. What we have to connect? OH. So now let's discuss. In this case, this carbon and this carbon, they are identical na? So use one type of symbol. These two carbons are identical. One possibility, I can attach OH to this carbon or this carbon giving same alcohol. Second possibility, I can connect to any one of them. Any one of them I'm saying, okay, I'm not saying both of them, I'm saying any one of them, you are connecting OH is giving same possibility. And next is this, how many different symbols are coming here? 3, means for this I can write 3 alcohols. For this 5 carbon chain I'm getting 3 alcohols. Then next, these two carbons are identical, one symbol, this is different, and this is also different. How many different symbols are made there? 1, 2, 3 and 4. Means in this case I can get 4 alcohols. Next case, in this case, these 4 carbons are identical. Okay, and here I can not connect anything. Why? There is no hydrogen to replace na yaar. So in this case, all 4 carbons are identical. So here I will get 1 alcohol. So how many alcohols are coming? 4 plus 3, 7 plus 1, 8 alcohols are coming. Is it clear or not? Examiner may ask one more question. Out of these 8 alcohols, how many are primary, how many are secondary, and how many are tertiary alcohols? That is very easy. You can find it. Okay or not? And I will make it simple. Whenever it is given like this, C5H11 given, this is a free valence to connect anything. Directly say 8 structural isomers are possible. C5H11 given, directly answer 8 structural isomers are possible. Without wasting your time, C5H11 given, directly answer 8 structural isomers are possible. If you are connecting anything here, it could be halogen, it could be OH, it could be NH2 or whatever it is given, doesn't matter. Is it clear or not? Okay. But it is for C5H11. Okay. Next one, very important problem. Problem 13.2 is very important. Okay. Next is what? Write IUPAC name of the following compounds. What is given to you? CH3 twice. What is given to you? CH3 twice C. CH3 twice C means what? CH3 carbon CH3. Then next what given? CH2, then carbon, then again 3 CH3 attached to the same carbon. first thing you have to write the structure correctly. If you're not writing structure correctly, how you can write the IUPAC name? Am I right? Writing a structure correctly is very important there. Okay. So now in this case, what we can observe? First of all, for IUPAC nomenclature, rule is firstly selection of parent carbon chain. First is a selection of parent carbon chain. Okay. First is a selection of parent carbon chain. For parent carbon chain selection, first is go for the maximum number of principal functional group, then go for the maximum number of multiple bonds. Multiple bond means carbon carbon double bond or carbon carbon triple bond. Then go for the longest chain, and then go for the maximum number of substituent. This is rule for the selection of parent carbon chain. In this case, there is no principal functional group, there is no multiple bond, so simply I can go for the longest chain. I think this is the longest chain. Then numbering. If I am starting numbering from this side, I am getting lower numbers 1, 2, 3, 4 and 5. So what I can say, 2, 2, 4 trimethyl, this is total 5 carbon, pent and single bonds, so ane. Okay. Next, also you can solve by the same method, so will not waste more time for this. Okay, let's move to this also. Okay, this also you can solve. I will not waste much time for this one. Okay, next is sodium salt of which acid will needed for the preparation of propane. Write the chemical equation of the reaction. What they are saying, sodium salt of which acid? You are knowing one constant. Let's say we have this carboxylate ion RCO minus Na plus. Then we have two cases. One case, if I am heating this with soda lime, it is giving product RH. And if I am going for the electrolysis, it is giving product RR. This is known as Kolbe's electrolysis. So if you have RCONA, if I am heating with soda lime giving RH, and if I am going for electrolysis giving RR. Now what they are saying, sodium salt of which acid will be needed for the preparation of propane. So if I want to prepare propane, I will take carboxylic acid of 4 carbons. Propane is 3 carbons. But I will take carboxylic acid of 4 carbons. Sir, why? You are knowing, if this compound is heated with soda lime, what will happen? This 3 carbon will become alkane CCC, and this will be removed as Na2CO3. This is removed as Na2CO3. Very simple na? So for very simple, I said what if you have RC, what I said to you, if you have RC, C double bond O minus Na plus, and you are heating with soda lime, you are getting RH na. It means if this has N carbons, then this product has NC minus 1 carbon na yaar. 1 carbon, this 1 carbon is gone, it is removed as Na2CO3. So obviously in this decarboxylation reaction, if you want to make alkane of 3 carbon, then I will take carboxylic acid or carboxylate ion of 4 carbons. If examiner asks which carboxylic acid can give propane, then we may have 2 answers. One answer, if I am using this compound CO minus Na plus, I am heating with soda lime. What will happen? This part is gone as Na2CO3. This part become alkane 1, 2, 3. Second possibility, if I have this condition, if I heat with soda lime, this part will be going. This part is going. What left? This part left na. This part means what? 3 carbon chain na propane. So propane can be prepared by these 2 sodium salt of carboxylic acid. These 2 are the possible answers. Only one given here in NCERT, sodium salt of butanoic acid. Okay. Next is Next, very important question. Write structures and IUPAC name of different structural isomers of alkene corresponding to C5H10. What is given there? C5H10. And you have written all structural alkenes. All structural alkenes. How many carbons are given? 5 carbons are given. So first possibility you can write 5 carbon. 5 carbon chain. Next possibility you can write 4 carbon chain. 4 carbon chain. Next possibility you can write 3 carbon chain. Now we have to put double bond there, na? So in this case, if I want to put double bond, one possibility I can put at this terminal. Next possibility I can put double bond here. Okay. Sir, we can place here also. This will be same as the previous. This will be, if I am writing like this, let's say I am writing like this. These two are identical. Okay. Likewise, if it is a 4 carbon, if I am placing double bond here or here, same. Let's say I am placing here. Next possibility, I can place double bond to this place, and next possibility I can write double bond here. Sir, what about 3 carbon? Okay, let's draw. If you are drawing double bond here, 1, 2, 3, 4, 5 bonds around carbon, is it possible? Not possible. So how many alkenes are coming? You can check there. 1, 2, 3, 4 and 5. 5 alkenes are coming for the formula C5H10. Okay, next is draw cis, and they are asking structural alkenes. If they are asking total alkenes or considering stereo, then we have to check geometrical isomerism also. But in this question, they are asking structural isomers of the alkenes. Draw cis and trans isomers of the following compounds. What is given to you? CHCl double bond CHCl. So cis means what we can write? Carbon, carbon, chlorine, chlorine, hydrogen, hydrogen. This is what cis. HH or ClCl. If you can observe, these two are appearing to be same side. It is cis, and if I am writing like this, it is a trans form of this compound. Okay, next compound given C2H5 CCH3 and CCH3 C2H5. So carbon carbon double bond cis form. I will keep same type of group, same side like this, and C2H5 C2H5 like this is what cis isomer. And if I write like this CH3 CH3, this is your trans isomer. This is your trans isomer. Okay. Next one. Write IUPAC name of the product obtained by addition reaction of HBr to the hex 1-ene. Hex 1-ene. Hex means 6 carbons. 1, 2, 3, 4, 5, 6 carbons. 1-ene means double bond at one position. 1-ene. Now one condition given in the presence of a peroxide, second given in the absence of peroxide. So let's think about the presence of peroxide, absence of peroxide. HBr given in the absence of peroxide. What will happen? HBr, na, you can write H plus and Br minus. HBr, you can write what? H plus and Br minus. What next? This pi bond will break and bind to this H plus. Pi bond break and bind to the H plus. Now what will happen? Plus charge is more stable on this carbon. So obviously, what will happen? This hydrogen bind to this carbon. So this plus will form. Next, what will happen? Br minus will attack on this carbon and you will get this product. While if it is same compound, carbon, 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 double bond carbon, treated with HBr in the presence of peroxide, this will generate bromine radical. This will generate bromine radical. What will happen? In radical present, so this bond will go for homolytic bond fission. This will go for homolytic bond fission. Now what will happen? What will happen? You can easily say that, sir, radical is more stable on this carbon. Radical more stable on this carbon, Br bind to this carbon. Opposite will happen in this case. Radical is stable on this carbon, Br bind to this terminal carbon. You will get this product. Okay or not? This is the answer. Now we have one simple method also for this type of problems. Sir, what is a simple method? Tell me that one. Okay, don't worry. I am telling you. What is given? Hex 1-ene given. Hex 1-ene given. Hex 1-ene given. Okay, Higgs 1 in given. Now listen. Now observe these two carbons. This carbon contains one hydrogen, this carbon contains two hydrogens. One rule is there known as Markovnikov rule. Markovnikov rule. What this rule is saying? Ki anionic part of the reagent bind with the carbon having less number of hydrogen. So only HBr given. Follow Markovnikov rule. So out of these two carbons, which carbon has less number of hydrogen? Sir, this carbon has less number of hydrogen. So bind Br to this carbon, means you will get this product. Now if condition given HBr peroxide, peroxide, this is following anti-Markovnikov. Now anti-Markovnikov means opposite to the Markovnikov na yaar. This carbon has less number of hydrogen, this carbon has more number of hydrogen. Select carbon with more number of hydrogen, means I will select this hydrogen. So 1 2 3 4 5 1 2 3 4 5 6, and I will bind a Br to this carbon. Method is very simple. I think it is clear to you. If HBr given, select the carbon of double bonded carbon having less number of H. HBr peroxide given, select carbon with more number of H. Okay, next one. Write structures of different isomers corresponding to the fifth member of alkyne series. Very important and very good question. First of all, what is given there? Write the structure of different isomers of corresponding to the fifth member of alkyne series. They are not directly giving formula. What they are saying, fifth member of alkyne series. So firstly, find the fifth member of alkyne series here. First of all, you have to find the fifth member of alkyne series, na? Sir, how to find, sir? So you must know first alkyne, simplest alkyne. Which alkyne is simplest? Who is the first member of alkyne series? Who is the simplest alkyne? Please reply. Who is the simplest alkyne? Please answer. Who is the simplest alkyne? Ethyne. Very good. Krishna Reddy, ethyne, C2H2, very good. Okay, ethyne. So simplest alkyne or first alkyne. See, they are not directly giving formula. You must know who is the first alkyne. First alkyne is C2H2. Ethyne, yes, or acetylene. This is a first alkyne. And how to find fifth alkyne? You are adding one CH2, becomes second alkyne. One more CH2, third alkyne. You are knowing homologous series. So second alkyne, third alkyne, fourth alkyne, fifth alkyne. Each I will add one CH2 here. So CH2 plus this one plus one CH2. So C2H2 plus CH2, it become C2H2 plus CH2, C2H2 plus CH2. So 2 plus 1, 3 carbons, and 2 plus 2, 4 hydrogens. Likewise here also one more CH2, one more CH2, one more CH2. So if I am reaching to this carbon, and one more thing you can observe, one simplest method also available. Okay, so by this method you can solve. I think it is clear to you. One simple method is there. Check please. First member of alkyne has 2 carbons. So second member is having 3 carbons. Third member having 4 carbons. Fourth member has 5 carbons. So obviously fifth member has 6 carbons na yaar. By this method also you can find first member of alkyne has 2 carbons. So second member of alkyne has 3 carbons. third has a four carbons, fourth has a 5 carbons, so fifth member has 6 carbons. So obviously fifth member of alkyne series will be what? C6, and general formula of alkyne you are knowing, CnH2n minus 2. So 6 into 2, 12 minus 2, 6 into 2, 12 minus 2, 10, C6H10. I think it is clear how to find the member. This is also directly they can ask, who is the sixth, who is the fifth member of alkyne series, who is the third member of alkyne series, who is the fourth member of alkyne series. We have to find only one thing, who is the first member of alkyne series. Okay, so finally I am getting formula C6H10. This member is fifth member of alkyne series. Then method is same, 6 carbon given, so one possibility, write 6 carbon chain, 1 2 3 6 carbon chain. Next possibility, write 5 carbon chain, 5 carbon chain. We have two possibilities. Then 4 carbon chain, 4 carbon chain. Here I am writing 4 carbon chain. We have these two possibilities for 4 carbon chain. Then we have to put triple bond this time. Alkyne, triple bond. One possibility I can put triple bond here in 6 carbon chain. Next possibility I can put triple bond here. Okay or not? 1 minute. This one. Number 1 position, number 2 position. And next possibility I can put triple bond here also. For this one, here can I put triple bond? Are not possible here. 5 carbon possible around carbon. 5 bonds around carbon possible, not possible here. Can I put triple bond here? No, sir. Can I put? Obviously, there is no possibility for this one. Okay, so ignore this. Move to this one. In this case, here I can put triple bond. Yes, here I can put triple bond. Can I put triple bond here? No. 5 bonds will come around carbon and not possible. Only one is there. This case, can I put triple bond here? Triple bond like this. Is it possible? Check na yaar. 1, 2, 3, 4, 5 bonds around carbon. Is it possible? Is it possible? Not possible na yaar. So obviously I cannot put triple bond here. Okay. So here also not possible. In this place, yes, I can write triple bond. And next possibility I can write triple bond on this carbon. For this one, can I write triple bond here? No, sir, not possible. By carbon cannot make 5 bonds na yaar. Carbon cannot make 5 bonds. But I can put triple bond here. This or this, same. Okay, this is clear. Okay, so you can check. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 different alkynes are possible for this. Sir, what to do for the exam? Directly memorize na yaar. It is a matter of only 4 or 5 days. You can memorize directly. If they are asking fifth member of alkynes, directly answer. How many alkynes possible? 7 possible. Why to waste time for this? Okay. Next one. Next question include almost all the reactions of this chapter. What they are saying, how will you convert ethanoic acid into benzene? Ethanoic acid into benzene. Ethanoic acid. This is your ethanoic acid. And they are saying to convert this into benzene. Sir, how we can convert? So you are knowing one reaction. If we have molecule acetylene is heated in red hot Fe tube. This is going to become benzene. Obviously, 3 molecules are required. So if I am able to convert this given compound acetic acid or ethanoic acid into acetylene, I can make a benzene. Simple na? If I am able to convert this ethanoic acid into acetylene, I can make benzene. Point is how I can make it acetylene. This is very important. In this case, if I treat this with NaOH, after treating with NaOH, this is going to become CH3. Okay, for this I will use Okay, what is given to you? CH3COH. If I treat this with NaOH, what will happen? This is going to become CH3, C double bond O minus Na plus. Sodium salt is formed here. Now I want two carbons. How I can go to the two carbons? I will heat this with soda lime heating. What will happen? I remove this CO and it become CH4. Sir, you said I want two carbons, you are going to one carbon. Wait, two carbons will also come. Treat this with Cl2H nu or Br2H nu. Free radical substitution reaction will happen. This will give you CH3Cl, CH3Cl2, CH3CH3. How it is possible? CH3Cl2, CH3CH3. How it is possible? Please answer. How this conversion is possible? How this conversion is possible? Please answer. Please answer. How this conversion is possible? CH3Cl2, CH3CH3. Yes, Wurtz reaction. Very good. Wurtz reaction means treat this compound with sodium in the solvent dry ether. Wurtz reaction. I said na, this conversion include almost all the concepts of hydrocarbon chapter. Now I have to bind one chlorine to this two carbon compound. For this I will use same Cl2H nu. What will happen? This is become chlorine. I want to bind one chlorine there. What I will give? Cl2H nu. Okay. Obviously one equivalent will be given, so one chlorine bind. Then I will treat this with alcoholic KOH. You are knowing alcoholic KOH is causing elimination reaction. Alcoholic KOH is causing elimination reaction. By elimination reaction, this is going to become CH2 double bond CH2. What alcoholic KOH will do? By you have this compound, I am writing like this. Alcoholic KOH is removing, this is chlorine leaving group, directly attached carbon alpha, next carbon beta. Alcoholic KOH will remove beta hydrogen. If this beta hydrogen remove this sigma bond, hit here and chlorine will go out. You will get this compound there. After getting this compound, I will treat this compound with Cl2, but not the presence of light. This time I want to break pi bond. If Cl2H nu given, pi bond will not break. Cl2H nu given, pi bond will not break. This time I want to break pi bond, so I will not take the condition of light. Or I will perform a reaction in dark and cold. Pi bond break, one chlorine bind to this CH2, another chlorine bind to this CH2. This becomes CH2ClCl. Now I am about to reach to the acetylene molecule HC triple bond CH. Now this is a very important. If you have vicinal dihalide, and you want to make alkyne, then we have two methods. First method, either give sodamide or give alcoholic KOH followed by sodamide. Either give sodamide or alcoholic KOH followed by sodamide. Now you got desired product. Now from this to benzene you are knowing here. What we have to do? We have to take this acetylene in a red hot Fe tube. This become benzene. Now in this case, one more thing I want to say. This conversion key, we have this molecule sodium salt of ethanoic acid and we want to go to the ethane molecule. One method I said, firstly go for decarboxylation, make methane, then CH3Cl, then Wurtz reaction. Second, directly also we can prepare this compound. Sir, how we can prepare? So who will answer? How I can go for direct conversion? How I can go for direct conversion? This to this, how I can go for direct conversion? Yes, very good, very good. Electrolysis, go for the electrolysis, coal-based electrolysis. Hydrogen gas will be released at cathode and this will form at anode. Is it clear or not? This is very important. Remaining story is same. Remaining story is same. So if you observe this particular reaction, this include all the concept, almost all the concepts of hydrocarbon chapter. Okay, this is a very important. Okay. So let's see anything left in hydrocarbon or not. So two reactions are very important: coal-based electrolysis and decarboxylation. Coal-based electrolysis, RCONA, electrolysis giving RR, and decarboxylation is giving RH. That is a very important. What I am saying, listen it again. What I am saying, if you have this R, if you have this compound RCO minus Na plus, for example, okay, let's say you have this compound. If you are going for soda lime heating, this will give you RH. And if you are going for electrolysis, this will give you RR. This is a very important. That's why when we were having sodium salt of ethanoic acid, I am going for electrolysis, I am getting CH3 by R group now CH3. And when I am going for soda lime decarboxylation, soda lime means decarboxylation, soda lime heating means decarboxylation reaction, I am getting CH4. This is clear. This is very important. Okay. In benzene, all carbon-carbon bonds are equivalent. All carbon-carbon bonds are equivalent. Okay, so this is done. Now, in case of aromatic hydrocarbon, in case of aromatic, we have benzene molecule. If it is treated with electrophile, this is going to bind, electrophile is going to bind there, it becomes this compound. This electrophile could be Cl plus, Br plus, R plus, R, C double bond, O plus, NO2 plus, SO3. Cl plus coming if I am taking Cl2, AlCl3, likewise Br2, Lewis acid, I2, Lewis acid will give I. R plus is coming when I am taking RCl, AlCl3. This is coming when I am taking RCOCl, AlCl3. NO2 plus is coming when HNO3 plus H2SO4 taken, which is known as nitrating, H2SO4 taken, which is known as nitrating mixture, and SO3 electrophile coming when concentrated sulfuric acid is used. These are the different examples of electrophilic substitution reaction. If you are taking RCl, AlCl3, this will generate electrophile R plus, which can go for rearrangement also. Okay, so these are the different electrophilic substitution reactions related to the aromatic compounds. And if you have benzene molecule, this benzene is treated with Cl2H nu, then what will happen? All pi bonds will break there, and this Cl bind here. All pi bonds will break, and chlorine bind to the carbon. This compound will form C6H6Cl6, which is known as benzene hexachloride, but it is not having any benzene. Now you will say, sir, you said Cl2H nu is not breaking pi bond. Yes, Cl2H nu not breaking pi bond, but in case of benzene it is a breaking. So as per your syllabus, benzene is the only compound. Benzene is the only compound. Benzene I am saying, I am not saying substituted benzene also. Benzene is the only compound as per your syllabus where Cl2H is breaking pi bond, otherwise Cl2H not breaking pi bond. So if examiner asks which hydrocarbon reacts differently with Cl2H, answer is simply benzene. If examiner asks which hydrocarbon react differently with Cl2H, answer is benzene, because other hydrocarbons are not breaking their pi bond in the presence of Cl2H, but benzene is breaking its pi bond in the presence of Cl2H. This is a very important concept. Okay, someone is asking, so I'm saying if plus M group is there, for example OH, OR, OC double bond OR, NH2, NHC double bond OR, alpha hydrogen cases, they are containing lone pair, na? This is alpha hydrogen. They are this is plus H. They are ortho para directing and activating. If minus M group present, for example NO2, C double bond OR, C double bond OH aldehyde, C double bond O ketone, C double bond OR, like this. So you can observe that A double bond B, 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 C double bond N. These type cases minus M, they are meta directing. And if it is halogen, it is ortho para directing due to its plus M and deactivating due to its minus I. If it is halogen, then ortho para directing due to plus M and deactivating due to minus I. Means in these cases electrophile prefer to bind at ortho and para, obviously separately most of the cases, and these cases electrophile prefer to bind at meta. In these cases, when minus M group is present, Friedel-Crafts reaction not observed. If ring is deactivated by minus M, then Friedel-Crafts reaction not observed. In aniline also Friedel-Crafts reaction not observed, but we can perform by some other method that we discuss separately in amines chapter. Okay, this is done. So hydrocarbon topic also done. Let's move to the next topic, which is class 12th, first chapter of organic chemistry, haloalkanes and haloarenes. Haloalkanes and haloarenes. Haloalkanes, haloarenes, first chapter of class 12th organic chemistry. If halogen is directly attached to aromatic ring, for example benzene, it is called haloarene. For example, let's say we have this condition. Haloalkanes and haloarenes. Okay. Okay. Now, let's say we have this condition. This is aromatic ring, benzene, and halogen directly attached to benzene. It is haloarene. But let's say we have this condition. Halogen is present, benzene also present in the compound, but halogen not directly attached to benzene. It is not haloarene. This compound is aromatic. But this is not aryl halide or not haloarene, because halogen not directly attached to aromatic ring or benzene. This is considered as alkyl halide. Very important. Okay. If carbon-carbon double bond is present and halogen directly attached to this, it is called a vinyl. If carbon-carbon double bond given, and halogen attached at alpha carbon of alpha position of carbon-carbon double bond, this is called allyl. This is called allyl. Carbon double halogen directly attached here, vinyl. Halogen directly attached to aromatic ring, aryl. Okay or not? These classifications are very important. You have this toluene molecule CH3. One hydrogen displaced by halogen. One hydrogen displaced by halogen. Two hydrogens left. In the place of hydrogen, you can take any hydrocarbon. It is called benzyl. It is called benzyl. Clear or not? Ha, sir. Yes, if you are taking in the place of which this is hydrocarbon, then also it is a benzyl. Name will change, primary, secondary, tertiary benzyl, but there will be benzyl only. Okay. Okay. So let's discuss the problems. Okay, and one more compound is very important in this case. One compound is very important. Oftenly it is ignored, but if examiner is asking, that will be new for most of the students. This compound. This case, if I am having 3 bromines, if 3 halogens are present and they are attached to the benzene ring, then we have multiple possibilities. But if I attach 1, 3 and 5 position, it becomes most symmetric molecule. This is known as a sim-tribromobenzene. Sim means symmetric. Sim means symmetric. Sim-tribromobenzene. They can ask, what is the IUPAC name of sim-tribromobenzene? What is the IUPAC name of sim-tribromobenzene? Answer you can easily observe there, 1,3,5-tribromobenzene. Okay. Others easy, but this is very important. Very important. Okay. So let's discuss the problems. First is given, draw the structures of all. Just now I explained few minutes back what they are saying, C5H11Br. If you are conceptually strong, this type of problems are time pass for you. What I said, if you have C5H11 and here it is a bromine, chlorine, OH or anything else, they are asking how many monobromo structural isomers possible for C5. They can ask this also, how many monobromo structural isomers are possible for C5H12. See, if I am writing monobromo structural isomer of C5H12, means one hydrogen replaced by bromine na yaar. It becomes C5H11Br. Few minutes back I said C5H11 given, directly answer 8 structural isomers. And how to find that also I explained. And then I said to you, other than asking how many monochloro structural isomers are possible for C5H12 or how many structural isomers are possible for C5H11Br, they can ask how many primary bromo compounds possible for C5H11Br, how many secondary possible and how many tertiary possible. That can also be asked by the examiner. Okay, so that's what we discussed earlier also in first chapter, basic concept of organic chemistry. Okay, what I said I'm repeating again. 5 carbon C5, first possibility 5 carbon chain, next possibility 4 carbon chain. 4 carbon chain, we have 2 possibilities. Connect like 5 carbon chain, 4 carbon chain, then 3 carbon chain. 3 carbon chain, 5 carbon chain, 4 carbon chain, only 1 possibility for the extra carbon, and then 3 carbon. Now we have replaced hydrogen by halogen. This and this, they are same. This and this same and this is same. Okay, 3 halogens, 3 different possibilities for this one. These 2 identical. This is different. This is different. This is different. This is different. 4 possibilities for this. In this case, all these 4 are identical. Only 1 possibility. You can clearly also, you can solve like this. If you're knowing this method, simple method, you can solve like this. 8 possibilities are coming if you are attaching something by replacing hydrogen. For example, bromine. But don't get confused. If they're asking how many isomers for C5H12, then answer is 3 only. How many isomers for C5H12? No, nothing is hydrogen not replaced by anyone. Hydrogen not replaced by anyone. Now they are asking how many isomers for C5H12. Answer is 3. Normal pentane, isopentane, neopentane. Don't get confused. C5H12, 3 structural isomers are coming. C5H11X halogen. Then it is coming 8. Clear or not clear? Please reply. Please reply. C5H12. C5H12. How many structural isomers are coming? Or how many isomers are coming? 3. And C5H11X. How many are coming? 8. Are you understood or not here? Please reply. Understood or not? Please reply quickly. Yes. Clear? Clear? Yes. Very good. Very good. Very good. Very good. This is very important. Sometimes we are doing mistake. And it is C5H11X. In the place of X, you are taking alcohol, then 11 alcohols will come. If you are taking chlorine, then 11 haloalkanes, chloralkanes will come. If you are taking bromine, 11 bromoalkanes will come. But if we are giving C5H12, we get 3 alkanes. Clear now? Now, what I said for C, now I am solving. Here I solved C5H11X. Now, other than this, they can ask how many primary, how many secondary, and how many tertiary. Very easy. Observe, this carbon is a primary. Don't write here also, it is identical symbol layer. So either write for this or for this. Don't write for both, otherwise you will count wrong. Okay, this is a secondary, this is a tertiary. These two are identical, write for anyone. Okay, I am writing for this is a primary. This you can also, this carbon is connected with 3. This will be tertiary. This is going to give you secondary alkyl halide. This is giving primary. Check there. All are identical. Write for anyone primary. So how many primary coming? 1, 2, 3 and 4. How many secondary coming? 2. Secondary coming how many? Sorry, this is also secondary. Sorry. This is also secondary. How many secondary coming? 1, 2 and 3. And 1 tertiary is coming. You can check here. You can check here. Primary 1, 2, 3, 4. 4 primary coming. This is primary. This is primary. This is primary. This is primary. 4 primary coming. How many secondary coming? Check please. 1, 2 and 3. 1, 2 and 3. Secondary 3 coming. And how many tertiary coming? 1. Got it or not? So is it required to write this many structures? Answer is no. Solve by the symbol method which I said. Solve by the symbol method what I said, you will get all answers. For alcohols, for haloalkanes. Clear or not? Understood? Please reply. Please reply. Understood or not? Please reply. Please reply. Understood this concept? Understood? Okay, very good. Okay. Let's move to the next question. What they are saying, write IUPAC name of the followings. Write IUPAC name of the followings. I will solve few so you can get the concept. Okay, I will not solve all of them because we have to discuss so many chapters now. Okay, what is the rule? What is rule for the selection of parent carbon chain? Firstly, go for the principal functional group, then go for multiple bond, then go for carbon chain, then go for substituent. Few functional groups are always a substituent. They cannot act as a principal functional group. For example, halogens, for example, nitro, for example, ether. They are always, they are functional groups. They are functional group, but they cannot be principal functional group. Halogen, nitro, ether, they are functional groups. Or I can make it simple. In case of organic chemistry, if you ignore alkane, all are functional group. So halogen, nitro, ether, they are functional group, but they are not principal functional group. So they are always acting as a substituent. They are always acting as a substituent. I think it is clear to you. If examiner asks halogen is a functional group or not, for organic chemistry, halogen is functional group or not? Yes, it is functional group. Is it possible to consider this as principal functional group? No, never, not possible. Okay, so now you are knowing the rule, you are knowing this one more concept which I said here. You can easily find the IUPAC nomenclature. What is rule? Firstly, go for the parent carbon chain which is including principal functional group. It is halogen here. It is not principal functional group. Then what next? Go for the multiple bond. Go for the multiple bond. So if I select this chain, you can clearly observe. You can clearly observe for this chain. 1 minute. If I select this chain, you can clearly observe multiple bond is included, and I am making longer chain also. Multiple bond included and longer chain also coming. Then come to the numbering. If I am going from this side, bromine getting number 2 and multiple bond getting number 3, 1, 2 and 3 like this. Obviously we have to give lower number to PFG first, then multiple bond, no PFG, then multiple bond. So obviously this numbering is wrong. If I am coming from this side, 1, 2, 3, 4, 5. This case my bromine is getting 4 number and multiple bond getting number 2. Bromine is substituent na yaar. Give lower number to PFG, no PFG, then give lower number to multiple bond. This is the correct numbering. Remaining to you can write 4 bromo, total carbon 5, so pent 2 ene. Come to the second case. I have to include this carbon because multiple bond there. This side no carbon. Okay, I am going this side, 1 carbon coming, going this side, I am getting 2 carbons. Obviously I come this side. This is my parent carbon chain. Numbering from this side 1, 2, 3, multiple bond getting number 3. Numbering from this side, multiple bond getting number 1. 1, 2, 3 and 4. 2 position is a methyl, 3 position is a bromo. Alphabetically B is coming before M na yaar. So 3 bromo, 2 methyl, 4 carbon, so bute, and 1 position is ene, 1 ene. Clear or not? Likewise you can solve next also. In this case, this is the multiple bond. I have to include this carbon, this carbon, this carbon, this carbon, this carbon, this carbon, they are included. 1, 2, 3, 4, 5. 4 bromo, 3 methyl, pent 2 ene. Likewise, you can think about all IUPAC names. Now here one very important concept. Bond length, carbon fluorine, carbon chlorine bromine, obvious here. Fluorine to iodine, size increases, bond length increases. This is not important here. Anyone can guess here. And obviously carbon iodine bond energy is less. Dipole moment is a very important. Dipole moment of CH3Cl is more than CH3F, more than CH3Br, more than CH3I. What I am writing here, please look at here. This is CH3Cl, then fluorine, chlorine, fluorine, bromine, iodine written. If dipole moment they are asking for methyl halides, who is the maximum? CH3Cl, then CH3F, then CH3Br, and then CH3I. If they are writing HF, HFSCl, HBr, HI, no abnormality. HF more delta En, more delta En, more dipole moment. Dipole moment given HFSCl, HBr, HI, HF is more delta En, more dipole moment. But if they are giving CH3F, CH3Cl, CH3Br, CH3I, then CH3Cl is more than CH3F. CH3Cl is more than CH3F. Very important. Very important. Okay, let's move to the next part. Okay. Through questions, we'll revise all concepts. Okay. What is given here? Carbon, this benzene given pH, CH double bond, CH2. HBr given, HBr given. Okay, what is given to you? pH. Okay, pH, it is hanging. Oh my God. I think we need to. Okay, okay. 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 So let's discuss this problem. What is given? pH, CH double bond, CH2. What is given? HBr given, H plus Br minus. This is carbon-carbon double bond. For this phenyl, I wrote pH. You are knowing. Out of these two carbons, this carbon has less number of hydrogen. Na? So bind bromine to this carbon. What will form? pH, CH, Br, CH3. What is the reason? Because carbocation will be more stable on this carbon. Okay. Next one. This is CH and this is CH2. CH and CH2. HCl means H plus Cl minus. Which one is having less number of hydrogen? This carbon has less number of hydrogen. So I will bind chlorine to this carbon. Markovnikov rule here. How many carbons? 4 carbons. 1, 2, 3, 4. This carbon will get chlorine and obviously another will get hydrogen. Next one is given. Now this time they are giving peroxide. What they are giving? A peroxide. So this carbon has 1 hydrogen and this carbon has 2 hydrogen. Peroxide given with HBr. And remember, peroxide if it is observed only with HBr. If HCl or HI given, solve as per Markovnikov rule. Okay. If HBr peroxide given, then only you have to go for anti-Markovnikov. So this carbon is having more hydrogen. So I will bind there. It becomes pH CH2, 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 Br. Anti-Markovnikov. Okay. Next one. Why is sulfuric acid? Okay. You are saying, sir, underline few important lines. So if you observe through question, I am recalling, I am revising the concepts. Okay. Okay. So what is the question there? Why is sulfuric acid is not used for the reaction of alcohol with Ki? Okay. So when we want to convert alcohol ROH into RX, alcohol into RX, alcohol to alkyl halide, we have multiple reagents. One minute. Okay. When we are converting alcohol ROH into RX, ROH to RX, we have multiple reagents. For example, I can use HCl ZnCl2. If it is 3 degree alcohol, then ZnCl2 also not required. Okay. If 3 degree alcohol, then ZnCl2 not required. We can use HI. HI is coming from NaI plus, let's say I want to bind bromine. Then HBr coming from NaBr plus H2SO4. You can use KBr also. this sulfuric acid is diluted. Next, if I want to bind iodine there by replacing the alcohol, then I will use NaI plus H3PO4. We can use PCl3 or PCl5 or SOCl2 to bind chlorine there. Out of them, SOCl2, it is SOCl2. PCl3, PCl5, SOCl2. Out of them, SOCl2 is the best method. Next, if I want to bind bromine there, other than HX, I can use PBr3, but PBr3 coming from red phosphorus plus Br2. Red phosphorus Br2, I can use red phosphorus plus I2 also. Red phosphorus Br2 is generating PBr3, which is known as in situ generation, and this is generating Pi3, which is also in situ generation of Pi3. So these reagents can be used for making alkyl halide from alcohol, but any one of them cannot be used to convert. Any one of them cannot be used to convert PHOH into X. This carbon oxygen bond of phenol cannot be broken by any one of them. 1, 2, 6, how many of right? Okay, no one can be used. Phenol cannot be converted into haloarene by any of the reagent used for the conversion of alcohol into alkyl halide. Reason you are knowing, partial double bond character and other reasons are also there. Or if I focus on your syllabus or NCERT, only one reagent is available. Only one reagent is available which can break carbon oxygen bond of phenol, that is zinc. As per your syllabus, as per NCERT, we have only one reagent which can break a carbon oxygen bond of phenol, that is zinc. So I think it is clear. Now they are asking question here. Sir, what they are asking, why is sulfuric acid not used during the reaction of alcohol with Ki? Means when you want to prepare HI, you are using H3PO4. It is NaI. Okay, NaI. Okay, you can write Ki also, no problem. Plus S3. We are using H3PO4 for the preparation of HI. Why not H2SO4? Reason is very simple. If I am using H2SO4, H2SO4 is good oxidizing agent, will react with the I minus and will oxidize this I minus into I2. And what is our target to prepare HI? Our target is to prepare HI. I think it is clear. So why H3PO4 used for the preparation of HI, not H2SO4? Not H2SO4. Answer is a very simple here. If I am using sulfuric acid, that will oxidize I minus into I2. Sir, we discuss in, it is explained to us in salt analysis that sulfuric acid can also oxidize Br minus. Then why you are using sulfuric acid here? What you read in salt analysis, concentrated sulfuric acid can oxidize Br minus into Br2. This is a dilute sulfuric acid. Dilute sulfuric acid taken, na? So dilute sulfuric acid will not oxidize Br minus into Br2 and I will get Br. Concept is very simple. If you want to make HBr, you can use dilute sulfuric acid, but if you want to make HI, what we are using H3PO4. Why we are not using sulfuric acid? Answer is very simple, to avoid the oxidation of I minus into I2. So for first one, why is sulfuric acid not used during the reaction of alcohol with Ki? Answer is to avoid the oxidation of I minus into I2. Next is write the structure of different halogen derivatives of dihalogen. So next question, write the structures of different dihalogen derivatives of propane. Very important question. Very important question. Very important question. Dihalogen derivative. Generally we are discussing about monohalogen derivative. Oftenly we are discussing about the monohalogen derivative. Now here they are asking, write structure of different dihalogen derivatives of propane. Propane means how many carbons? 3 carbons. 3 carbons. What they are saying? Not saying monohalogen. If they are saying monohalogen, we got answer by symbol. One symbol this, another symbol this. 2 come for monohalogen. Very easy question. If they are saying monohalo derivative of propane, time pass question here, by symbol only 2 answer coming. They are not asking monohalogen derivative. They are asking dihalogen derivative. What they are asking? Dihalogen derivative. Focus on this term. Dihalogen derivative. Dihalogen derivative of propane. Very important question. Why very important? I think it is clear to you. Oftenly we are discussing about monohalogen derivative, but here they are asking about dihalogen derivative. How to solve? Here I cannot solve by making symbols. I have to solve by writing structures. I have to attach two halogens. Let's say chlorine. One possibility I can attach like this. Firstly, think about geminal cases. Geminal to you are knowing there. Two halogen attached to same carbon, gem dihalide. So firstly think about the geminal cases. These are the two geminal cases. Then think about the vicinal cases. In vicinal, we have one possibility attached like this, chlorine, chlorine, and then attached like this. This is not vicinal, this is not geminal. This is neither geminal nor vicinal. This is geminal, geminal, vicinal. This is neither geminal nor vicinal. These are the four possibilities coming. No, not three, four. You can check that. It is there in front of you only. It is there in front of you only. Check na yaar. This is a chlorine. Arey yaar, my handwriting is not good na. Arey yaar, I am teaching to the future doctors, and doctors' handwriting to you are knowing how good their handwriting is. So I am influenced by the future doctors. That's why my handwriting is something like this. Okay. So now you can check there. How many dihalogen derivative are coming for the propane? Answer, it is there in front of you. 4 are coming. Next, among the isomeric alkanes of molecular formula C5H12, identify one that of photochemical. Okay, understood. What is the question there? C5H12 given. They're asking which isomer of C5H12. Okay, I am not Dr. VSP. I am just VSP. Okay, no problem. Focus here. What is the question there? Among the isomeric alkanes of molecular formula C5H12, identify the one that on photochemical chlorination yields a single monochloride, 3 isomeric monochloride, 4 monochlorides, 4 isomeric monochlorides. Very important question. First of all, I need to think about the number of isomers of C5H12. Please answer. How many isomers are possible for C5H12? How many isomers are possible for C5H12? How many isomers are possible for C5H12? Please reply. Yes, very good. 3. Very good. Excellent. 3. Very good. Total 3 isomers are there for the C5H12. First possibility 5 carbon chain, next possibility 4 carbon chain, and next possibility 3 carbon chain. Now their question is, which isomer will give single monochloro product? So where I can make only one type of symbol. In normal pentane or in isopentane or in neopentane, where I can make only one type of symbol. Normal, iso or neo. Which pentane? Neo. Very good. Here I can make only one type of symbol. So this will give one single monochloride. This is your neopentane. So answer is what? Neopentane for first one. Second question, 3 isomeric monochlorides. So tell me please, out of, so 1 gone, 2 left. Normal pentane, isopentane. So out of isopentane, normal pentane, when I can draw 3 different symbols. Second question is 3 isomeric monochloride. Na? So where I can draw 3 different symbols. Yes, normal. Very good. Excellent. You are doing excellent. Very good. Excellent. This case. So this is the answer for second. Here I can write 3 monochloro derivatives. Next question, 4 isomeric monochlorides. Here I can draw 4 different symbols. 1, these 2 are identical. Don't count them as a 2. They are identical. 1, 2, 3 and 4. So for this one, answer is this. Okay, so you got the method how to find this type of problem without writing the structure. Just make symbols, you'll get answer. Next one, draw the structure of major monochloro product in each of the following reactions. Just now I explained all the concept. You can easily find answers for these time pass questions. Let's do quickly. Let's solve them quickly. SOCl2, what I said, if you want to convert ROH into RX, I said 6-7 reagents there. Okay, let's solve one. First case, what will happen? SOCl2 given. What will happen? This OH replaced by chlorine. OH replaced by chlorine. This become cyclohexyl chloride or chlorocyclohexane plus SO2 plus HCl. So when I am using SOCl2 as a reagent, it is giving this product plus SO2 plus HCl. They are gaseous byproducts. That's why SOCl2 is the best method. Examiner may ask which is the best method for the conversion of alcohol into alkyl halide or alkyl chloride. Answer is SOCl2 is the best reagent, thionyl chloride. Name of SOCl2 is thionyl chloride. An examiner may ask why it is the best reagent. Answer, its byproduct SO2 and HCl, they are gaseous in nature. Easy question. Number 2, Br2H nu given. Whenever Br2H given, whenever Br2H or Br2O heat or X2H or X2 heat given, then bind halogen by removing hydrogen. Bind halogen by removing hydrogen at the most stable radical. Got it or not? Whenever X2H or X2 heat given, bind halogen at most stable radical by removing hydrogen. So now observe here. If I remove this hydrogen, this radical form, if I remove this hydrogen, I will get radical here. And radical on benzene highly unstable. So obviously this I will not consider. Out of this 1 and 2, which radical more stable? Obviously this radical is more stable layer. This radical will be stabilized by resonance. Very good. So obviously we have to bind bromine here by displacing this hydrogen. So what a product will form? Or I can make it simple here. If Cl2H given, then bind halogen at the alpha position of carbon-carbon double bond or adjacent carbon of carbon-carbon double bond. So this is having carbon-carbon double bond. This is adjacent carbon. They are bind halogen by replacing hydrogen. Simple method. Next one. Now this is a very important. This is one OH. This is another OH. This is the OH directly attached to benzene. So this will not react. I said na. Carbon-oxygen bond of phenol can be broken only by one reagent, that is zinc. This too I can replace here. If I replace this OH, in the place of this OH, what will come? Cl. That is the answer. This OH remains as it is. Solve this one. Hi given, H plus I minus, carbon-carbon double bond, this carbon is having, it is not having any hydrogen, so less hydrogens are present for the zero hydrogen. Obviously iodine bind with this Markovnikov product. So iodine bind to this carbon, Markovnikov product. Now this is what? Br given, NaI acetone given. It is a Finkelstein reaction. Solvent dry acetone. They can give acetone also. Means dry acetone is a better answer, but they are saying acetone, that is also correct. Okay. What will happen? Bromine replaced by iodine. Product will be what? CH3, CH2I. Simple reaction. Bromine displaced by iodine. Now observe again. Br2 heat or light given. Just now I said na X2H nu given. Then bind halogen at the adjacent carbon or alpha carbon of double bond. So this is carbon-carbon double bond. This is alpha. This is alpha. Select any one alpha. Select any one alpha. See, I'm selecting any one. Then obviously I'm selecting this one. This is going to bind Br because both alpha are identical. If they are given two equivalent of bromine, then bind bromine to this carbon also. I said earlier, yeah, X2H nu. X2H nu is not breaking carbon-carbon double bond. Only one example is there where X2H nu or Cl2H nu breaking carbon-carbon double bond, that is a benzene. That's what we discussed, benzene hexachloride. Okay, so I think this is very easy and it is clear to you. Next is density part is very important. So if one chlorine present, density less than water. Density less than water. 2 chlorines or more, 2, 3, 4 like this. 2 or more chlorines present, minimum 1 bromine present, minimum iodine present, then density more than water. Okay, 1 chlorine, density less than water. 2 or more chlorines, minimum 1 bromine, minimum 1 iodine, density more than water. Solubility. Haloalkanes are very less soluble in water, but they are highly soluble. They can be easily dissolved. Haloalkanes tend to dissolve in organic solvents. They are very slightly soluble in water, but they are significantly soluble in organic solvents. Arrange the compounds in the increasing order of boiling point. What first given? Bromomethane. Bromomethane means CH3Br. Bromoform means CHBr3. Chloromethane CH3Cl, and dibromomethane. Dibromomethane means CH2Br2. In general, as molar mass increases, van der Waals attraction increases, boiling point increases. For same type of functional group. In general, if molar mass increases, van der Waals attraction increases, so boiling point increases if functional group is of same type or same. So now check that. CH3Br 1 bromine, CH3Cl 1 chlorine, CHBr3 3 bromines and CH2Br2 2 bromines. So in this case, minimum molar mass for CH3Cl. So CH3Cl is having least boiling point, then CH3Br, then CH2Br2, and then maximum for CHBr3. So it is answered based on the molar mass. More molar mass, more van der Waals attraction, force, more boiling point. Next one. What is again? 1 chloropropane. 1 chloropropane. 1 chloropropane. Okay, 1 minute. 1 chloropropane. 1 chloropropane. 1, 2, 3. This 1 chloropropane. Isopropyl chloride. Okay, I will write only this. Isopropyl chloride. And 1 chlorobutane. Now, how to solve this type of problem? Structure itself is giving answer. Structure itself is giving answer. Check the surface area. Check the surface area. More surface area, more interaction. More surface area. More surface area, more van der Waals attraction, more boiling point. Check here. This is the surface area for this. This is the surface area for this. And this is the surface area for this. Where I have maximum surface area. Where I have maximum surface area. Please answer. It is there in front of you only. Where surface area is maximum. 1 chlorobutane, isopropyl chloride, or 1 chloropropane. Who is having maximum surface area? Yes, third. Obviously third. So this is having maximum. So let's say I'm ranking them as 1, 2, and 3. So maximum surface area for 3. Then 1. Yes, maximum surface area for 3. Then for 1. Then for 2. This is the order of boiling point. This is the order of boiling point. So boiling point mainly depends on two factors: surface area and molar mass. More molar mass, more surface area. More molar mass, more surface area, more van der Waals attraction, more boiling point. And if these structural forms are given, you can find by surface area directly. Next, you are knowing if it is alkyl halide, OH minus directly attack and Cl directly, it is called SN2 reaction. It is a bimolecular reaction and its order molecularity is 2 and order is also 2. In this case, this trigonal bipyramidal transition state is formed. Trigonal bipyramidal transition state is formed, which is having this sp2 hybridized carbon. And in this case, what will happen? If Cl present right hand side, OH will come left hand side, means inversion of the configuration is observed in SN2 reaction. So what are the properties of SN2? In this case, attack of nucleophile and removal of leaving group taking place simultaneously. First point. Second point, trigonal bipyramidal transition state is formed. Trigonal bipyramidal transition state is formed. Carbon is sp2 hybrid for this transition state and inversion of the configuration is observed. And one more point here, inversion doesn't mean optical inversion. Inversion means general configuration is inverted. Means if Cl present right, OH will be left. Okay, inversion doesn't mean in SN2 inversion of optical rotation. Inversion means general configuration is inverted. This is about the SN2 reaction. You can clearly observe here they are writing this representation for the SN2 reaction. This nucleophile attack, this will leave, and here it is the trigonal bipyramidal transition state. While in case of SN1, it is going to make carbocation. In case of SN1 reaction, it is going to make carbocation intermediate. Okay. Now these two are given. Check this carbon. This is sp3 carbon, bromine, iodine, chlorine. All 4 groups or atoms are different. If tetrahedral center is surrounded by 4 different atoms or group of atoms, it is called chiral center. And if one chiral center present, one chiral carbon or chiral center present, compound is always optically active. One chiral center always optically active. So it is optically active na yaar. And if it is optically active, its mirror image will be non-superimposable. So these two are non-superimposable mirror images. And non-superimposable mirror images are known as enantiomers. Known as enantiomers. Okay. So next one. Now these 4 molecules are given and we have to find the order of reactivity for SN2 reaction. We have to find the order of reactivity for SN2 reaction. What I said for the SN2, in SN2 nucleophile attack directly na yaar. Nucleophile attack directly on the carbon center, halogen leave. So it is affected by the steric hindrance. Here you can observe chinna atoms are attached, hydrogen, chinna atom. How they can provide a steric hindrance? In this case, we have this one CH3 group. Here we have 2 CH3 groups. And last case, we have 3 CH3 groups. More hysterically hindered, this one. So attack of nucleophile become difficult na yaar. SN2 will be less. SN2 will be less in last one, 3 degree. This small atoms, less hindered, attack easily. SN2 will be more attack, direct attack, easy to attack. So order of reactivity for SN2, first, then 1 degree, 2 degree, and then 3 degree. So how to find reactivity for SN2? Steric hindrance more, SN2 reaction, or reactivity for SN2 reaction less. Simple. In case of tertiary butyl or 3 degree, if you check NCERT data, they are saying no SN2. SN2 reaction is 0 in case of 3 degree. SN2 reaction is 0 in case of 3 degree as per this NCERT data. Okay. So if examiner asks which alkyl halide is not undergoing for SN2 reaction or have zero SN2 reaction? Answer is tertiary. Answer is a tertiary, 3 degree. Clear or not? But if I am observing SN1 reaction rate, it will be just opposite. 3 degree become more reactive for SN1. Is it clear or not? Okay. Okay, next one, SN1. As I said earlier, for the SN1 reaction, what is formed? Carbocation intermediate is formed. So your alkyl bromide or alkyl halide will break into carbocation and bromide ion. So this carbocation intermediate is formed. Carbocation intermediate is formed during SN1 reaction. First point. So obviously, if carbocation intermediate is more stable, it will be easily going for SN1 reaction. Then second step, this nucleophile attack on this carbocation and your product will form. First step of the reaction you can observe is reversible. Examiner may ask, first step of SN1 reaction is answer reversible. Okay, so let's observe. Let's observe the reactivity order. You can clearly check there. As I am going from 3 degree to 2 degree to 1 degree to CH3X, SN2 increases, SN2 increases, but SN1 increases towards 3 degree na. So SN1 reaction is more in 3 degree than 2 degree and then 1 degree, while SN2 reaction is more in 1 degree than 2 degree and then 3 degree. SN1 is more in 3 degree. SN2 is more in 1 degree. And as per NCERT data, 3 degree is not going for SN2 reaction. If carbocation is directly attached to benzene like this, or this condition means allyl carbocation or benzyl carbocation given, they are stabilized by resonance effect now. And since they are stabilized by resonance effect, they are stable carbocations, they have high probability of SN1 reaction. Okay, if it is given RCl, RF, RCl, RBr, Ri. So obviously Ri bond is a weak bond in IR. It is a weaker bond. Weaker bond means what? It is easier to break. Easier to break means what? More reactive. RF bond, it is a stronger bond here. Stronger bond, difficult to break. Difficult to break. Less reactive. So Ri more reactive, RF less reactive. You can answer by two methods. One, you can say for Ri bond energy is less, that's why more reactive. Or iodine minus iodine, I is good leaving group. I is good leaving group. I is good leaving group. This also an answer. So if examiner asks why Ri more reactive than RF, we can give two answers. One, I can say bond energy low, or I can say iodine is good leaving group. Okay. So now let's discuss these problems. In the following, okay. Firstly, you try. 1 minute is given to you. Keep on solving, keep on learning. Okay. 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 So let's solve. What they are asking? SN2 reaction faster. Where SN2 is faster? What we are knowing? SN2 affected by the steric hindrance. Check here. Check here. This chlorine is 1 degree. This is 2 degree here. Or this carbon hindered by these two. This is hindered by only one. So 2 will hinder more. Reactivity will be less. This is more reactive. Carbon iodine, carbon chlorine. Which bond is easier to break? Carbon iodine. Or which one is a better leaving group? Iodine. So obviously this is more reactive. This case. Okay. Okay, done. Solve. Next one. Predict the order of reactivity of the following compounds in SN1 and SN2 reaction. The 4 isomeric bromobutanes. Butane, 4 carbon. First of all, I have to think about the isomers of bromobutane. One possibility 4 carbon chain, next possibility 3 carbon chain. Bromobutane means I have to bind a bromine then. Here I can write 2 different symbols. So for this I can write 2 possibilities. Here these 3 are identical and this is different. So for this also I can write 2 possibilities. One possibility this and second possibility this. These are 4 different isomeric bromobutanes. Now I have to find the reactivity for SN1 and SN2 reaction. For SN2, how it is affected? Steric hindrance. So where steric hindrance maximum? Check here. These are the 3 CH3 groups. Steric hindrance maximum. This is least reactive. So I am writing 1, 2, 3, 4. Fourth least reactive for SN2 reaction. SN2 I am solving. SN2 I am solving. Then where steric hindrance minimum? Obviously this case is steric hindrance minimum. This is primary also. So 1 is most reactive. Out of 2 and 3, this bromine you can also, this is 2 degree, this is 1 degree. This is hindered from 2 sides. 2 is less reactive than 3. So 2 less reactive than 3. Simple. This is order of SN2. How to check SN1? By the stability of carbocation. Make carbocation here by removing bromine. Remove this bromine and make carbocation. Remove this bromine, make carbocation. Remove this bromine, make carbocation. This carbon is highly stable because of more number of alpha H. This is most reactive. So number of alpha H you can count. So based on the stability of carbocation, you can find the stability for reactivity for SN1. This has 9 alpha H. For this carbon we have only this 1 alpha H. For this carbon we have 2 plus 3, 5 alpha H. And for this carbon we have 2 alpha H. So this fourth is most reactive, then your 2, then 1 and then 3. This is the reactivity for SN1 and SN1 and SN2 for this. Next question. pH CH2Br. What is given here? pH. 1 minute. What is given first? pH. pH CH2Br. C6H5 means phenyl. pH CH2Br. Next is given pH. If you write structure properly, you will get answer. pH Br. This is your second structure. Third is given pH CH CH3 Br. And last one is given PHC CH3 PHBr. pH means what? C6H5. pH means C6H5 here. So now we have to check steric hindrance for SN2 reaction. So see, this is most hindered, least reactive. Out of these two, who is more hindered? This is C6H5, this is also C6H5. And this is CH3. This is C6H5. Now this is 6,5 C6H5 common. 6 carbon will provide more hindrance or 3 carbon? Obviously 6 carbon provide more hindrance, na? So less reactive for SN2. This is least hindrance, so most reactive for SN2. So this is most reactive. 1, 2, 3, 4. 1 is most reactive for SN2 and 4th is least reactive for SN2. Out of these two, how to find? Very easy, yaar. This is CH3, this is C6H5. 6 carbons will provide more hindrance than 1 carbon. So less reactive, na? So 2 is less reactive than 3. SN1 reaction order opposite based on the stability of carbocation. Okay. Similarly, you can solve next problem also. Why to waste time for this? Let's move for next one. I said if one chiral carbon present, then it is always optically active. One chiral carbon always optically active. Okay. Now they're asking identify chiral and achiral molecule of the each following pair. I said one simple method here. One simple method. One chiral carbon present always optically active. One chiral carbon always optically active. Now check first. This carbon H, CH3, Br, OH, all 4 different. One chiral carbon always optically active. It is a chiral. These two bromines are same. It is a chiral or not chiral. Check this carbon OH, H, CH3 and this all 4 different chiral. Likewise, you can solve others also. This case left this CH2, CH3, this CH2, CH3 same chiral. Likewise, you can solve next also. Why to waste time for this one? Okay. Next one. Okay. No questions. So I will revise few concepts here. SN1 I already explained. If alcoholic KOH given and reacting with RCl, RBr, Ri, or I can generalize Rx treated with alcoholic KOH. This will go for elimination reaction and product will be alkene. Remove beta hydrogen. That's it. Remove beta hydrogen. If this Rx is treated with aqueous KOH or NaOH, we'll go for SN reaction. Your product will be alcohol. Depending on the nature, it will be SN1 or SN2. Okay. For example, is primary taken SN2, tertiary taken SN1. In case of 2 degree depends on the solvent. Water taken SN1, DMSO taken SN2. Okay. So Rx, alkyl halide, may go for elimination reaction or substitution reaction depending on your reagent. If your reagent is alcoholic NaOH or KOH, it will go for elimination reaction. Alkene will form as a major product. While if you are going for aqueous KOH reaction, in this case, this alkyl halide going for substitution reaction or nucleophilic substitution reaction and giving alcohol as a major product or alcohol as a product. Okay. Grignard's chemistry is a very simple, very easy. Grignard reagent is RMgX. Metal, magnesium is a metal, so it is a plus and R is a minus. How it is prepared? Answer is very simple. Alkyl halide treated with magnesium in solvent dry ether. You have to heat Rx with magnesium in solvent dry ether. This is Grignard's reagent. R is a delta minus, Mg is a delta plus. Grignard reagent, R is a delta minus, Mg is a delta plus. So if a Grignard reagent, R delta minus, Mg delta plus is treated with those compounds who are having acidic hydrogen, for example, hydrogen attached to sulfur, for example, let's say RS taken, water taken. If remember this one, remember this trick Sona tags. Hydrogen attached to sulfur, hydrogen attached to oxygen, hydrogen attached to nitrogen. Terminal alkyne and hydrogen attached to halogen. These are acidic hydrogens. Yeah. So if hydrogen attached to sulfur, hydrogen attached to oxygen, hydrogen attached to nitrogen, terminal alkyne and hydrogen attached to halogen, they are called acidic hydrogen. They are the first law of Grignard. If any one of them given, for example, I am taking RSH, hydrogen attached to sulfur, I am taking water, hydrogen attached to oxygen, I am taking RNH2, hydrogen attached to nitrogen, I am taking RCOH, hydrogen attached to oxygen, I am taking terminal alkyne and I am taking HCl, hydrogen attached to halogen. If any one of them taken, Sona tags taken, hydrogen attached to sulfur, hydrogen attached to oxygen, hydrogen attached to nitrogen, terminal alkyne and hydrogen attached to halogen. If any one of them taken, what will happen? They will give H plus. Grignard giving R delta minus. This minus plus combine, what will form? RH will form. What will form? RH will form. Very important. If you are giving any of these condition, it is going to make RH. If it is, let's say, this Grignard reagent is a PHMgX, then this will give what? PHH with these, and PHH is what? PHH is a benzene. PHH is benzene. Is it clear or not? For example, let's say I have this condition. I have a chlorobenzene. 1 minute. Wait. Okay, let's say I have chlorobenzene. Someone is saying, convert this chlorobenzene into benzene. Convert chlorobenzene into benzene. How I can convert? Firstly, treat with Grignard's reagent, magnesium Firstly, treat with magnesium in solvent dry ether. Convert this into Grignard. So you will get PHMgCl. Polarity of Grignard reagent is a very important. If you are able to write correct sign of charge plus or minus, your answer will be correct. Now magnesium is metal delta plus and this carbon is delta minus. Now give anyone who can give acidic hydrogen. For example, I said, so hydrogen attached to Sona tags, I said, Sona tags, hydrogen attached to sulfur, hydrogen attached to oxygen, hydrogen attached to nitrogen, Ta means terminal alkyne, hydrogen attached to halogen. Give any one of them. Let's say I'm giving water. For make it simple, I am writing water as H plus OH minus. This writing is not correct, but okay, we can get answer. Now observe, this benzene phenyl part has minus charge na yaar. This is minus charge, so bind with plus. PH minus H plus, it become PHH. Obviously it is benzene na yaar. So how I can convert chlorobenzene into benzene? I think it is clear to you. This is one part of the Grignard chemistry. Second part of the Grignard chemistry. If Grignard's reagent given RMgX given, it is treated with formaldehyde. What will happen? R is minus, Mg is a plus. R is minus, Mg is plus. Arey minus will attack on plus na yaar. What minus will do? Minus will be searching for plus. In this formaldehyde, this oxygen is minus, this carbon is a plus na. This R is minus. Minus will bind with plus. This R minus attack on this pi bond break. When this break, you will get what? R, this is CH2, and this become O minus, minus bond with MgX. And when water is added to this become RCH2OH. Means formaldehyde is reacting with Grignard reagent, making primary alcohol after hydrolysis. In this case, in the place of this RH, if it is R, then here R will, if it is R, then what I will get? RCHROH, secondary alcohol. And if this H is also R, means ketone, I will get tertiary alcohol. Means I can say when Grignard reagent RMGX, is treated with formaldehyde followed by water, it is giving RCH2OH, primary alcohol. Next, when this Grignard's reagent is treated with any aldehyde other than formaldehyde, then two R groups are there, this R and this R. So this will give RCHROH, secondary alcohol. And when this is treated with ketone, RC double bond OR, followed by addition of water, it is giving you tertiary alcohol. So if I say all aldehydes are giving primary alcohol when treated with Grignard's reagent, true or false? All aldehydes are giving primary alcohol when treated with Grignard's reagent, true or false? Please reply. All aldehydes are giving. No, not true. False. Because we have one aldehyde who is giving primary alcohol. Formaldehyde giving primary alcohol. Other aldehydes are giving secondary alcohol. So now, and this ketone is giving tertiary alcohol. So now if I am saying, please listen, if I am saying all aldehydes are giving secondary alcohol when treated with Grignard's reagent, true or false? True or false? False. But if I say all aldehydes except formaldehyde giving secondary alcohol with Grignard, true. Which aldehyde giving primary alcohol with Grignard? Formaldehyde. And all ketones are giving tertiary alcohol with Grignard's reagent. This is the chemistry of Grignard. Very beautiful chemistry. Okay. So this Grignard part is clear. Next is ESR reaction. There is no need to discuss much about the ESR reactions. What we discuss, let's say this is a chlorine or any other halogen. This chlorine is ortho-para directing due to plus M and deactivating due to minus I. So when electrophile is given, this is going to bind at para position and ortho position. Obviously, out of ortho and para is a major. In general, in case of ortho para directing groups, para is a major. In general, in case of ortho para directing groups, para is a major. After knowing this reaction is a time pass na yaar. So let's visit the reactions quickly. Chlorobenzene, okay, this is SNAR that we discussed separately. Okay, so ESR concept I think clear to you. ESR concept is clear. Next is SNAR. SNAR reaction very easy. What will happen in SNAR? Let's say we have this chlorobenzene. This chlorobenzene has a partial double bond character as well as sp2 hybridization for this carbon. Because of partial double bond character and sp2 hybridization, bond energy of this carbon halogen bond is high. In this case, if I am making this carbocation, it is highly unstable carbocation, and pi electron density is a repelling nucleophile. Because of all these reasons, in this case, SN reaction is not observed in ordinary conditions. SN reaction not observed in ordinary conditions. But in drastic condition, we can have SN reaction. So what is the meaning of this? So let's say we have this chlorobenzene. Let's say we have this chlorobenzene. This chlorobenzene is treated with NaOH. There is no reaction. No reaction. No reaction. Why no reaction? Just now I explained. Partial level bond character and sp2 carbon will make it high bond energy. Phenylium carbocation highly unstable and nucleophile rebelled by pi electron density. These reasons will making it not fit for the SN reaction. But if I am giving NaOH at high temperature like 350 degrees Celsius temperature and 308 atm pressure, in the place of 350 degrees Celsius temperature they can write fusion also. Fusion means melting. Temperature is obviously high. What will happen? Now this Cl will be displaced by this OH, and when this Cl displaced by this OH, it becomes phenoxide. Sir, OH is displacing Cl. How it become phenoxide? It is a phenol, sir. No. One concept is there. One concept is a very important concept. Very important concept. Let's say we have this alcohol. Alcohol treated with NaOH. This is not going for reaction. But if it is a phenol, phenol reacts with NaOH, making a phenoxide. So if it is given like this, RCl, NaOH, first of all, high temperature not required, and second product will be ROH, alcohol. But if it is given PHCl, and if you want to react with NaOH, first of all, high temperature and pressure required. Product will be phenoxide. Why phenoxide? Because phenol which is formed will react with the NaOH of medium and become phenoxide. And if you want to convert this phenoxide into phenol, you need to go for acidification, give H+. I think this is clear. This reaction is called SNAR. We are doing substitution reaction, nucleophilic substitution reaction in aromatic compound. SN, nucleophilic substitution reaction, AR in aromatic compound. Okay, so in this case, how I can increase the reactivity for SNAR? Answer is very simple. If you are able to bind, listen properly, how we can increase reactivity for SNAR? Answer is very simple, by binding electron withdrawing group at ortho and para. If you bind electron withdrawing group at ortho and para, reactivity for SNAR will increase. Reactivity for SNAR will increase. For example, check properly. First case, required temperature 623 Kelvin, means 350 degrees Celsius. Next case, 443 Kelvin. Next case, 368. And here, last one, reaction possible only by warm water. Means, in case of haloarenes, SNAR reaction can be increased by electron withdrawing group. Can be increased by electron withdrawing group at ortho and para. If you are binding electron withdrawing group at ortho para, reactivity for SNAR will increase. SNAR I am saying, not ESR. Electrophilic substitution reaction rate increased by electron donating. ESR means electrophilic reaction. It is increased by electron donating group. Its reaction increased by electron donating. SNAR increased by electron withdrawing group. So we can observe no electron withdrawing, 350 degrees Celsius, 623 Kelvin. One electron withdrawing group attached, 443 Kelvin required, less temperature required. Two electron withdrawing, lesser temperature required. And if, the most important one, if you are having 2,4,6 trinitrochlorobenzene, what you can check there? This reaction is possible without strong heating. I am not saying without heating. Listen properly. I am not saying without heating. What I am saying? Without strong heating. Heating is required. Now what is written there? Warm water. Warm. some heating required, nearly 40 degrees Celsius temperature required. I am not saying no heating, I am saying strong heating not required. So you can clearly observe this 2,4,6-dinitrochlorobenzene is giving picric acid without NaOH. Without NaOH, taking NaOH will make phenoxide, then you can make phenol by giving H+. Without NaOH and simply by taking water as a nucleophile. And without strong heating, some heating required. Examiner may ask which chlorobenzene can go for SNAR reaction in ordinary conditions or without drastic conditions. Answer is 2,4,6 trinitrochlorobenzene. Sir, what about meta, if electron withdrawing group attached at meta position? If electron withdrawing group attached at meta position, then as per NCRT, no effect. No effect on reactivity is observed by the presence of NO2 group at meta position. No effect. With that, talking about which reaction? SNAR reaction. So as per NCRT, no effect is observed by the presence of NO2 group at meta position. Okay, some effect is observed, but that is negligible. Okay. Okay, in this case, examiner may ask for SNAR reaction, how many steps are there? 2 steps. First is slow, second is fast. Intermediate has a 3 RS, and intermediate, in intermediate you can check your Cl and OH bonded together and you cannot make complete circle here. It is partial delocalization of minus electron density. So this SNAR completed, and I think this chapter also completed. Last is okay, ESR reactions I said earlier. Chlorine is ortho-para directing, so bind at ortho and para major. Like Cl2LCl3 given, chlorine bind at para major. HNO3H2SO4 given, NO2 bind at ortho and para major. H2SO4 given, SO3H bind at ortho and para major. Then CH3Cl and hydrochlorCl3 given, this will generate electrophile CH3 plus. It is binding at ortho and para major. Then CH3COCl given, this is generating electrophile. This is generating electrophile CH3C double bond O plus. This is binding at ortho and para major. This is done. Now I said earlier only ki chlorine, bromine, iodine, they are, or halogens, in general halogens, they are ortho para directing due to their mesomeric effect, and they are deactivating due to their inductive effect. That is explained in this question. Okay. Then you are knowing Wurtz reaction na yaar. Wurtz reaction you are knowing. In the place of Wurtz reaction is for RX, alkyl halide. If you are taking PHX, same reaction, sodium diether. Sodium diether, it is making PHPH. It is known as Fittig reaction. And if one is RX and another is a PHX, and sodium diether taken, PHR form, this is known as Wurtz Fittig reaction. Simple yaar. RX, sodium diether, RR, this is Wurtz reaction. In the place of alkyl halide, aryl halide taken, Fittig reaction. Now alkyl halide taken plus aryl halide taken, alkyl halide, Wurtz, aryl halide, Fittig, Wurtz, Fittig reaction. Simple, very easy. Okay, so this is done. Okay. I explained how to find reactivity for SN1 and SN2. Based on this, you can solve this problem. I explained Grignard concept also. This is given. What will happen? Magnesium bind here, it becomes MgBr. Water given, H bind to this, it becomes cyclohexane. Second problem also you can solve based on the concept which I said. Last problem, let's discuss last problem. Okay. So, okay, let's discuss this problem also. RBr given, magnesium. So this is going to be what? R MgBr. In the place of H2, they are giving D2O. So D2O, I can write what? D plus and OD minus. RMgX, R minus. Now check. R is minus, D is plus, minus plus bind, minus plus bind. It become RD. Simple na yaar. Okay. So now, based on this, we have to find R groups. You can easily find what is the, where D is binding. D is binding here na, means this R is your CH3 CH3. So here firstly Mg came, then deuterium came. I think it is very easy to understand. Understood na? Next one, RMgX given. sorry, Rx given, this is making D and D is making E. This side is a very important. This Rx sodium ether is giving this compound. We have to think what this Rx is. So this Rx to this RR is a Wurtz reaction. So how to think? Cut this molecule in two equal halves. So left half or right half you have to take. Let's say I'm taking this part. So this is what? So this Rx is your actually CH3C, CH3X. This is your Rx. Now you can easily Rx become RR. By this become combined RR. Now forward side you have to think magnesium diether given what will happen? This is going to become CH3C, CH3, CH3, MgBr. Then water given. So I said now in Greek art if you're writing polarity correctly you will get answer. Carbon is delta minus, magnesium delta plus. Water I am writing H plus OH minus to make concept easy. Check here. This carbon is a minus na bind with H plus. Carbon minus bind with H plus. This is going to become what? CH3, CH, CH3, CH3. This is your product E. So I think this is very easy to understand. Only this part is important. Rx making this. So how to find Rx? This is your Wurtz reaction. This is your Wurtz reaction. Cut this equally. Left, right you can easily find. Okay. This is about polyhalogen compound. Revise it properly. Few terms are very important. Few terms are very important. Revise it properly. Okay. DDT is also very important. It is a fat soluble compound that's stored in fat tissues, and that is why going to the next trophic levels. Okay, next chapter is alcohol phenol ether. Okay, so before alcohol phenol ether I am giving break of 5 minutes. So take break of 5 minutes. Okay, so it's 10:15. So we resume our class at 10:20. You have 5 minutes. Okay, so 5-minute break. 5 minutes break. 10:15 a.m. to 10:20 a.m. Audio, video, okay? Please check audio. Video to okay. Reply about the audio. Is it coming? Okay. So precise. The exam which you are preparing for is game of time management. Okay. If you are able to manage time properly, na, then automatically you can improve 40 to 50 marks just by proper time management. Okay, so our next topic is alcohol, phenol, ether. As you are knowing, we are covering NCERT, important topics, important points. For NEET 2024, MSD-7. Okay. So, are you ready? Are you ready? Shall we start? Okay. Okay. Just 5 days to go, sir. These 5 days can create big difference if you're able to manage your time, if you're able to consolidate the concepts properly. Then you can score good, you can cross your cutoff marks, even though if you are at lower mark region in this stage also. Managing remaining days is very important. Don't waste your time in traveling. And firstly, complete your exam and everything, then go from here and there, no problem. Okay, so let's start the discussion. Question is, classify among the following as a primary, secondary and tertiary alcohols. So you can check this carbon. This carbon is attached to only one carbon, means this is a primary alcohol. You are knowing carbon attached to one carbon, primary. Carbon attached to two carbons, secondary. Carbon attached to three carbons, tertiary. So this carbon is a primary. So primary alcohol. This carbon also primary. This carbon primary. This carbon is a secondary. Observe. This carbon is connected to these two carbons, na? So this is secondary. This carbon is connected to these two carbons, so secondary. This carbon is connected to 1, 2 and 3 carbon. This is tertiary. Okay, so this is the primary alcohol, primary alcohol, primary alcohol, secondary alcohol, secondary alcohol, tertiary alcohol. Next, they are writing, identify allylic alcohol in the above example. I said to you that carbon-carbon double bond, if adjacent carbon or alpha carbon is having halogen, then allylic halide. If it is alcohol, then allylic alcohol. Simple layer. So observe. This is a carbon-carbon double bond. Its alpha carbon has OH. This is allylic. They are saying allylic alcohol. So this is allylic. There is no double bond in this. No double bond in this. No double bond in this. This is carbon-carbon double bond. And this is OH attached to the adjacent carbon of double bond. This is also allylic. Now someone will say, sir, what about this, sir? Sir, what about this? This is carbon-carbon double bond of benzene. That will not be considered for allyl. Carbon-carbon double bond of benzene will not be considered. Here I am considering this carbon-carbon double bond to say this is allyl alcohol or allylic alcohol. This is carbon-carbon double bond of benzene. It will not be considered for the allylic. So what is the easiest way to avoid the confusion? Make circle for this pi electron cloud of benzene. So no confusion. No confusion. Now you can observe. This is your secondary benzyl alcohol. It is your secondary benzyl alcohol. Next question. Next question. In case of phenol, common name and IUPAC name both are same. This is very important. One principal functional group, common name, IUPAC name same. This compound is also very important. It is named as a hydroquinone, hydroquinone or quinol. This name is also very important. Here it is also very important. PHCOCH3 is known as anisole. And if it is PHO C2H5, it is called phenetol. So these two names are very important. Phenetol and anisole. These two names are very important. IUPAC name I will not discuss. Okay, because it is already discussed, na? Okay. So, okay, let's solve this. I'll discuss few examples so you get idea about the IUPAC nomenclature. Now, in this case, this is alcohol. This alcohol is principal functional group. So this carbon must be included in PCC. This side, I am getting longer chain 1, 2, 3, 4, 5. This is my longer chain, no multiple bond present. This is my parent carbon chain. This is PFG. I have to give lower number to this 1, 2, 3, 4, 5. 4 is a chloro and 2 and 3 they are methyl. So 4 chloro, 2, 3 dimethyl, total carbon 5. So pent single bond. So N and it is ol. So pentane 1 ol. Now in this case when I am writing name, I am saying 4 chloro, 2, 3 dimethyl, pent N 1 ol. Here it is N pentane 1 ol. So whenever A, E, I, O, U, Y is present, whenever A, E, I, O, U, Y is present before in, ein, this E is dropped. So this is a pentane and O is present, this E will be dropped. So it will be only AN, that's it. This is the only one important concept, others are you are knowing properly. So you can check that. This is they are writing pentane 1 ol. Here it is no E. E is not there because actually it was N 1 ol. What I said, if it is A, I, O, U, Y before N, then this E is deleted or A is dropped. It become AN only. Okay. Second example, it is ether. So you can check left side 3 carbon chain, right side 2 carbon chain. Obviously 3 carbon chain will be selected because any side we don't have multiple bond. 1, 2, 3. So it is what? 2 position is what? Ethoxy group. So 2 ethoxy propane. This case OH is a principal functional group. So it is one going any side is same. So 1, 2, 3, 4, 5 and 6. So 2,6 dimethyl. 2,6 dimethyl benzene 1 ol, or you can simply say phenol also. In this case, nitro and ethoxy, we are knowing nitro ethoxy, ether and nitro group, both are functional group, but they cannot act as a PFG. They are always a substituent, So in this case, going from this to this side or this same number coming, so alphabetically it is ethoxy, this is nitro, so 1 and 2. So it is 1 ethoxy, 2 nitrocyclohexane. Likewise, you can think about next also. Here, bond angle is very important. In case of dimethyl ether, this bond angle is more than 109 degree. In dimethyl ether, bond angle is more than 109 degree. Next one. Grignard reagent chemistry, I explained earlier only. So, okay, what is given? Give the structures of the and IUPAC of the product expected for the following reactions. Catalytic reduction of butanol, al written, al means aldehyde, al means aldehyde, ol means alcohol. So what will happen? Catalytic reduction of butanol, 1, 2, 3, 4 carbon, butanol. Catalytic reduction means reacting with H2 in the presence of catalyst, nickel, palladium or platinum. What will happen? The CO group is reduced into alcohol. means this is going to become CH2OH. So it becomes butane 1-ol. Hydration of propene in the presence of dilute sulfuric acid. Propene, carbon-carbon double bond, dilute sulfuric acid given. Dilute sulfuric acid given means what? It is H2OH plus. H2OH+. What is the easiest way to solve? It is a CH3, this is a CH, this is CH2. H2O given, I can write H plus OH minus. Now check here. This carbon has 1 hydrogen, this carbon has 2 hydrogens. Markovnikov rule is saying that anionic part of the reagent bind with the carbon having less number of hydrogens. So will this OH, anionic part will bind to this carbon, means my answer will be CH3, CH, OH, CH3. Next is given reaction of propanone with methyl magnesium bromide followed by hydrolysis. So what is that saying? Reaction of propanone. This is your propanone. Propane and one means ketone. So obviously this is the condition here. Reacting with methyl magnesium bromide, CMGBr. Actually it is CH3MGBr. 1 minute. Okay. 1 minute. What is again propanone? CH3 C double bond OCH3 treated with CH3MGBr. Grignard reagent magnesium plus CH3 minus. This carbon is plus. This minus attack on this plus, pi bond will break. So what will happen? This becomes CH3 CH3. This CH3 bind to this carbon na CH3 and this become O minus. O minus is bonded with MgBr plus. When water added, this O minus become OH. So what product you will get? This tertiary alcohol will be formed. Few minutes back only we discussed the chemistry of Grignard's reagent. Then preparation of phenols. We already discussed कि chlorine is good leaving group, SO3H is also good leaving group. So if SO3H is attached to benzene or chlorine attached to benzene, they can be converted into phenoxide and acidification will make it phenol if they are treated with NaOH in the strong heating conditions. Okay. Next. Industrial method of preparation of phenol from cumene. Cumene, oxygen, this cumene hydroperoxide formed and that become phenol. This intermediate is a very important. Let's discuss the in-text problem. How are the following alcohols prepared by the reaction of suitable Grignard reagent on methanol? Methanol means what? H C double bond OH. I want to make this. So observe this part, CH2OH. This part is coming from methanol layer. So only focus on this part. This part is coming from Grignard. CH2OH part is written, means coming from Grignard. Coming from this formaldehyde. CH2OH coming from formaldehyde. This is coming from formaldehyde. Check formaldehyde. CHHO. It is a CH2 and 1 oxygen. So CH2OH part coming from formaldehyde and remaining part coming from the Grignard. So now you can show this part I will write Grignard means CH3 CH CH3 MgX and remaining you are knowing this will react and how to form product you are knowing. Observe next one, CH2OH part will be coming from CH2OH part is coming from CH2OH part is coming from HC double bond OH means methanol. So this part is coming from Grignard. So for this part what I can write? MgX. Remaining story you are knowing. Okay. Next one. Write the structure of product of the following reactions. What is given here? H2OH plus. H2OH plus. To make it simple, you can write H plus OH minus. Actually, in case of H2OH plus, nucleophile is water only, not OH minus. If H2OH plus given, nucleophile is a water. I am writing to make it simple. How to find? Carbon-carbon double bond given. CH2, Markovnikov product, where OH will bind? Obviously to CH carbon. This will form in first reaction. Second reaction, NaBH4. NaBH4 can react with aldehydes, ketones, acid halide, halides and alkyl halide. Alkyl halide. Aldehyde, ketone and acid halide, they become alcohol. They become alcohol. And alkyl halide, when treated with Grignard's, this NaBH4, this become alkane. This become alkane. RH. So NaBH4 is reacting with aldehyde, ketone, acid halide, making them alcohol. Alkyl halide can also react with NaBH4 and become alkane. Simple yaar. Now find. This is your ester. This will not affected by NaBH4. This is your ketone. Will be affected by NaBH4. NaBH4 react with aldehyde, ketone, acid halide. This ketone will react na yaar. And when this ketone react, this become alcohol, and this ester is not affected by NaBH4. Second, this is aldehyde. This react with NaBH4. Aldehyde, ketone, acid halide. They react with NaBH4, become alcohol. So this become alcohol. So what will form there? CH3, CH2, CH, CH3. This CHO becomes CH2OH alcohol. Simple yaar, very easy concept. Next one. Next problem. Arrange the following set of compound in the order of their boiling points. Arrange the following set of compounds in the order of their increasing boiling point. Okay. One concept I am telling to you. If they are giving similar molar masses or sometime exactly same molar masses, if you have comparable molar masses, then boiling point of carboxylic acid is more than the boiling point of alcohol. Alcohol is having more boiling point than aldehyde or ketones. Aldehyde and ketones. Aldehyde. So this concept you can apply for next topics also. And aldehyde and ketones. Out of aldehyde ketones, in general, ketones are more than aldehydes. And then it is ether and alkane. Ether alkane comparison is very interesting. If alkane is having 1 carbon, 2 carbon, 3 carbon or 4 carbon, up to 4 carbons in alkane, boiling point of ether is more, and 5 carbon onwards, boiling point of alkane is more. What is order of boiling point? Carboxylic acid more than alcohol, alcohol more than aldehyde ketone more than, obviously yaar, someone is asking picric acid is more than alcohol. I am not writing acidic strength, lala. I am not writing acidic strength, I am writing boiling point. Arey yaar, listen properly. What is written here? Boiling point for similar or comparable molar masses. Boiling point. Not acidic, boiling point. So listen, carboxylic acid more than alcohol more than aldehyde ketones. Aldehyde ketones, generally ketones are more. And ether alkane depends on carbon count of alkane. In general, as per our syllabus, I am telling this story. So up to 4 carbons of alkane, ether is more. 5 carbon onwards, alkane is more. So after knowing this, you can easily solve this problem. What they have given: pentane 1 ol, pentane 1, 2, 3, 4, 5 carbon 1 ol, butane 1 ol, butane 1 ol, butane 2 ol, butane 2-ol, and next is given ethanol. Next is given propane 1-ol, and next is given methanol. All are alcohol. All are monohydric alcohol, means all have one OH group, one OH. Then how to find? Simple, by surface area. Check, this is having maximum surface area, followed by this. So maximum boiling point for this, I am giving numbers. Then number 2 will be this, number 3 will be this. Now check, this is having how many carbons? 3 carbons. This is number 4. This is number 5, and this is your number 6. I think you got the concept. More molar mass, more surface area, more van der Waals interaction, more boiling point. Okay, next one. This is clear. This problem is clear. Okay, next one. N-butane, normal butane, ethoxyethane, pentanal, and pentane 1-ol. Alcohol more than aldehyde. So I'm giving numbers this side. Let's say A, B, C, D written. A, B, C, D written. Alcohol more than aldehyde. Aldehyde more than ether and alkane. Out of ether alkane, how to compare? Carbon count. How many carbons are present in this alkane? 4 carbon now, means ether is more. Up to 4 carbon of alkane, ether is more. So B is more than A. Okay, this is the question. Very good question. Next problem. Arrange the following compounds in their increasing acidic strength. Propane 1-ol, it is alcohol. 2,4,6 dinitrophenol, 3-nitrophenol, 3,5-dinitrophenol. And okay, I will tell you one simple concept. Carboxylic acids are more acidic than phenols. Phenols are more acidic than alcohols. Alcohols are more acidic than terminal alkynes. Terminal alkynes are more acidic than terminal alkenes. This is the acidic strength order. For same functional group, minus M minus I, same functional group, minus M minus I will increase the acidic strength. Different functional group solved by this. And picric acid is more acidic than carboxylic acid. Simple. By this you can easily find the acidic strength concept. Okay. Write the structures of major products expected from the following reaction. What is given there? Mononitration of 3-methylphenol. So now in this case, this OH is plus M group, so it is ortho-para directing. This is ortho position of OH and this is the para position of OH. CH3 is also ortho-para directing due to plus H. For this CH3, this is the ortho position and this is the ortho position. These are the ortho positions of CH3 and this is the para position of CH3. So obviously both are directing to same places. This binding is difficult because 2 groups are there, so entry is difficult. So one possibility I can attach an O2 group here, another possibility I can attach to this. So I will get 2 possibilities or two major products can be formed. One major product you can write this, and second major product you can write this one. That's what written here. So I think it is very easy to find. Next one, dinitration. Now, if I am doing dinitration, just now we discuss, this OH is saying to go to these carbons, CH3 also saying to go to these carbons. So this binding is difficult, so ignore this one. One possible bind here, second possible bind here. Dinitration. Okay. Next is given mononitration of phenyl methanoate. Phenyl methanoate. Phenyl ethanoate. Okay, this is phenyl ethanoate. They are giving answer as per phenyl ethanoate and writing here methanoate. Okay, so I am writing this molecule. This is a phenyl and this is 2 carbon ethanoate. Phenyl ethanoate. Now this oxygen is going for resonance plus M. So ortho-para-directing. So NO2 binding at para is major. Okay. Next question. Give structures of the product would expected when each of the following alcohol react with HCl, ZnCl2, HBr, SOCl2. What is given? Butane 1-ol given. Treated with HCl, ZnCl2. It is 1 degree alcohol, will go for simply SN2 reaction. Going for SN2 means what? Replace this OH by Cl directly. Don't apply much concept, simple concept. 1 degree SN2, OH replaced by Cl, that's it. HBr also same, SOCl2 also same. Then next given 2-methyl butane 2-ol. 2-methyl butane 2-ol. This is 3 degree. HCl ZnCl2 will make carbocation there. SN1 reaction. This will not go for rearrangement, already stable. Cl minus bind here. Okay. HBr also same. SOCl2 given. SOCl2 is not able to generate carbocation. You can directly answer in the place of OH, you can write Cl. That's it. In the place of OH, you can write Cl. Okay. Next one. Predict the major product of acid catalyzed dehydration of 1-methyl cyclohexanol and butane 1-ol. What they are saying? 1-methyl cyclohexanol. This is your cyclohexanol and its one position. Its one position has CH3 group. Acid catalyzed dehydration means what will happen? H plus is given and heating also done. H plus coming from concentrated sulfuric acid, not from HCl. If HCl is coming, it will go for previous case. OH replaced by chlorine. HBr also same, HI also same. It is coming from concentrated sulfuric acid or from concentrated phosphoric acid. OH will give lone pair to this H plus. This is going to generate this OH2 plus oxonium ion. This will leave, this will make this carbocation. This is CH3, this carbon form. You cannot rearrange it. So I have two possibilities. I can make double bond here, second I can make here. This double bond will be more stable because of more number of alpha. This will be my major product. So what will happen? This CH bond will break due to heating and double bond will come here. This alkene will form as a major product because it has more number of alpha hydrogens. Next is butane 1-ol. Butane 1-ol given. H plus heating given. Lone pair bind with this H. It is going to become OH2 plus. Because of heating, OH2 plus will leave. It become this carbocation. This will rearrange to this place. Now, one possibility I can break this CH bond, another possibility I can break this CH bond due to heating. These are the two possibilities, 1 or 2. Possibility number 1. Okay, I'm writing here. This carbocation is formed. Now, for this we have two possibility. I can break this CH bond due to heating. I can break this CH bond due to heating. obviously this CH bond is giving most of alkene, so this will be your major product and this will be your minor product. Okay, next one. Ortho and para nitrophenols are more acid than phenols. Ortho, why? Ortho para nitrophenols are more, I said na, same functional group like phenol, phenol, phenol. Then minus I, minus M increases acidic strength. Write equation involving the following reactions: Riemann-Tiemann reaction, Kolbe's reaction. In Riemann-Tiemann reaction, what we are doing? We are taking phenol treated with CHCl CHCl3 in the presence of KOH followed by acidification. This is giving salicylaldehyde as a major product. In this case, one more question may be asked by the examiner: who is the electrophile? So electrophile in this case is a dichlorocarbene. What second is written? Kolbe's reaction. Kolbe's reaction. In Kolbe's reaction, what we are doing? We are taking phenol. This phenol is firstly treated with NaOH to make it a phenoxide, which will increase the reactivity of benzene ring. So it can react with weak electrophile, carbon dioxide or dry ice. Then it is going for acidification. This is giving you salicylic acid or as a major product. Okay. So these are the two important reactions: Kolbe's reaction and Riemann-Tiemann reaction. Next one. Some commercially important alcohols you can read. Next, Williamson's ether synthesis concept. I will explain you simple concept. Let's say we have this ROH. We will treat this with sodium, so it become RO minus Na plus. This RO minus Na plus is treated with alkyl halide. Which alkyl halide? Primary alkyl halide or 0 degree, for example CH3Cl. NCERT is writing 1 degree for 0 degree also. Okay. For example, if they are asking methane is having 0 degree carbon, 1 degree carbon, please answer 1 degree carbon as per NCERT. Don't answer 0 degree carbon, because NCERT is writing carbon not attached to any carbon or attached to one carbon is 1 degree carbon. Okay, so what will happen? This, if it is 1 degree, 0 degree, then this will attack and Cl will leave. And what will form? ROR prime. Ether is formed. This is known as Williamson's ether synthesis. Williamson's ether synthesis. Williamson's ether synthesis. So Williamson's ether synthesis observed when it is 1 degree alkyl halide or 0 degree alkyl halide. Very easy to memorize. William 1 degree, 1 degree, 1 degree, Sun 0 degree. Alkyl halide going for ether synthesis with reagent RO minus. After knowing this, you can easily solve all the problems given here. They are saying, I want to prepare this compound. Point is how I can prepare. Tertiary butyl, ethyl tertiary butyl ether is given. How I can prepare? We have two choices. One choice, I can take this alkoxide ion O minus Na plus treat with this one. Or I will focus on the main part of the reaction. Okay, this one. Second choice, take this and this one. What we discussed, Williamson ether synthesis is giving ether as a major product if it is 1 degree or 0 degree alkyl halide. This is your 1 degree alkyl halide. Yes, this will give you ether. This will give you ether. This is 3 degree alkyl halide. This will not give ether. In 3 degree ether not form. At least in 2 degree ether form less. Minor product. 3 degree no ether. This will give only alkene. Means what will happen? This will remove this beta hydrogen. This will come here and Cl will leave. It will give alkene as a product. Okay. Okay, next one. So this question, I think it is clear to you. Next question. Okay, reactions with HI, ether, ROR. It is a least reactive functional group. Very important line written here in NCERT. Ethers are least reactive functional groups. Since they are least reactive functional group, that is why cleavage of ethers take place with concentrated HI or HBr at high temperature only. Is it clear now? Ethers are least reactive functional group. How to find the concept for the reactions of ether? Very easy method. ROR prime given, treated with HI. Obviously heating required. Without heating also you have to solve, but if they are asking specific question, then say heating is required. What first thing will happen? This lone pair bind with this H plus. What it is giving? ROR prime H plus. Now, how to decide reaction? If it is, let's say one part is good for SN1, another part is good for SN2, then net reaction will be SN1. Net reaction will be SN1. One is good for SN1, another good for SN2, then net reaction SN1. If both are good for SN1, then we have to find who is better for SN1 by stability of carbocation. Stable carbocation will go for SN1. If both are good for SN2, then we have to find who is better for SN2. How to find? Less hindered will go for SN2. Less hindered will go for SN2. Point is who is going for SN1? 1 degree SN1, 3 degree, 3 degree SN1, 1 degree SN2. If you are able to develop allyl carbocation or benzyl carbocation, they are also going for SN1. And 2 degree also going for 2 degree is going for SN2 reaction in case of ethers. So 1 degree, 2 degree, SN2. Very easy to memorize. SN2, 2 cases, 1 degree, 2 degree. Other cases, SN1. That's it. After knowing this, you can solve the problems. So what problem given here? Let's check. First is given. Now check it quickly. First is treated with HI. So first of all, this O bind with hydrogen, this become O plus. This is 1 degree, which reaction? SN2. This is also 1 degree, which reaction? SN2. Both are good for SN2. Then how to find steric hindrance? Who is less hindered? This is less hindered. It will go for SN2. I minus directly attack on this carbon and this will break. So this part become iodide and this part become alcohol. First is solved. Second case, this is 1 degree, good for SN1. Good for SN2. 1 degree, good for... this is, I am repeating again. This is 1 degree, good for SN2. This is 1 degree, good for SN2. If both are going for SN2, find who is better for SN2. How to find? Less hindered. Who is less hindered? This is less hindered. So I minus will directly attack on this carbon. So this will leave. This part become iodide and this part become alcohol. Check this one. This is 1 degree, good for SN2. This is 3 degree, good for SN1. First step, H bind here, it become oxonium ion of ether. It is good, one good for SN1, other good for SN2 means SN1 takes place. How SN10 takes place? This bond breaks. So this part become, you can check, this HO is going with this one. This part become alcohol and this part become iodide. Okay, I think it is clear to you. Next one, this is given. Now you can check, this oxygen directly connected to benzene. This bond never break. Partial level bond character and everything you're knowing. So obviously this bond will break. If this part break, what will happen? Oxygen remains bonded with benzene. So this part become phenol. This part become phenol. And this part become iodide. Next one, okay, this is done. Next one, ESR reaction same as chlorobenzene is also orthoparadirecting. This is any small molecule. OCS is orthoparadirecting. So two products form ortho and para measure. Okay. Next one, write the reaction for Williamson ether synthesis of 3-ethoxy 3-methyl pentane Starting from the ethanol and 3-methyl pentane 2-ol. What they are saying? Ethanol. This is ethanol. 3-methyl pentane 2-ol. Okay, we need to again restart it. Okay. Okay, so what is given here? What is given here? Ethanol and 3-methyl pentane 2-ol. Ethanol and 3-methyl, total 5 carbon pentane, 3-methyl and 2-ol. So 2 position ol and 3 position methyl. Now, point is I have to prepare ether from this. So what Williamson saying? 1 degree alkyl halide required. Na? So if I replace this OH by Cl, that will be 2 degree alkyl halide. If I replace this OH by Cl, this will be 1 degree. So I will do one thing. I will treat this with SOCl2. So this become alkyl halide because I want 1 degree alkyl halide for ether synthesis by Williamson's method. And this I will treat with sodium metal. So this become ethoxide and remaining, you know, this will attack and Cl will leave, ether will form. So what is important? Selection of the alcohol to make alkyl halide. What is the concept? Williamson's ether synthesis, 1 degree alkyl halide required. That's it. Okay, so this is done. Treat the products of the following reaction with H+. As I said earlier, we have to solve directly. H plus Br minus given, O bind with this H plus, this is 0 degree good for SN2, this is 1 degree good for SN2. If both are good for SN2, then go for less hindered. Who is less hindered? CH3 less hindered. So now Br minus directly attack on this and this will break. So this part become alcohol and this part become CH3Br. Here what we can check, this oxygen is connected to the benzene or phenyl. This oxygen will not leave, means this bond will break. So this side become phenol and this part becomes CH3 C2H5Br. Simple. If oxygen is connected to phenyl ring, this is not leaving, partial double bond character is there. So this oxygen part become phenol and C2H5 part become bromide. This is what? This is a phenol molecule, is ortho-para directing. This is NO2 plus electrophile. This will generate electrophile NO2 plus ortho-para directing. So obviously NO2 bind at para and another bind at ortho-para major. Okay, I said HI reaction. You can easily solve this last problem also. Okay, this we discussed earlier. This problem we discussed. Question number 4 is here. This we discuss here. This problem already discussed. Okay, 1 minute. Yes, this problem we discuss. The same concept we discuss. Okay, so this is alcohol phenol ether completed. Next chapter, aldehyde and ketones. Aldehyde ketones and carboxylic acid. Aldehyde ketones and carboxylic acid. First, give the name of the reagent to bring out the following transformation. Hexane 1-ol to hexanal. What is given? Hexane 1-ol to hexanal. Now this is primary alcohol to aldehyde. We have to take mild oxidizing, this is oxidation na? Mild oxidizing agent, for example PCC or CrO3 in anhydrous condition. CrO3 in anhydrous condition. We have to take mild oxidizing agent. Because if you are taking a strong oxidizing agent, this alcohol will oxidize up to carboxylic acid. PCC can be taken or CrO3 anhydrous can be taken. If you have to take one, then prefer PCC. Next one, cyclohexanol to cyclohexanone. This is cyclohexanol and we want to make a cyclohexanone. This is also oxidation. In this case, it is a ketone. Ketones are not going for oxidation in ordinary conditions. Listen, I am not saying they are not going for oxidation. What I am saying, ketones are not going for oxidation in ordinary conditions. Ordinary conditions. Or ketones can be oxidized in drastic conditions. Drastic conditions means strong oxidizing agent and heating. So this conversion possible by mild oxidizing agent like PCC. It is possible by strong oxidizing agent also, for example KMnO4 H plus or K2Cr2O7 H plus or CrO3 H plus. But don't heat, otherwise ketone will also oxidize. So preparation of aldehyde is possible from alcohol, primary alcohol is possible by mild. But preparation of ketone from alcohol is possible by secondary alcohol is possible from strong as well as mild. But if you are taking strong, avoid heating otherwise ketone will also oxidize. Next problem, 1-fluorotoluene to parafluorotoluene to parafluorobenzaldehyde. Okay, so one reaction is there. I will tell you that reaction directly, then you can go for any conversion. We have this molecule, methylbenzene or toluene. This I want to convert into benzaldehyde, CHO. Then we can go for Itard reaction, CrO2Cl2 in solvent carbon disulfide followed by hydrolysis. We can go for other reactions also. For example, firstly treat with CrO3 in the presence of acetic anhydride followed by hydrolysis. And in industry, you can go for this conversion by treating firstly with Cl2H 2 equivalent followed by hydrolysis. This is the industrial method. Once you know this, you can easily think what they are saying. Parafluorotoluene means you have this condition. And you have to make this one, parafluorobenzaldehyde. How it is possible? CH3 to CHO conversion. Just now I said go for Itard reaction, go for chlorination followed by hydrolysis, side chain chlorination followed by hydrolysis, or you can go for CrO3 acetic anhydride followed by hydrolysis. Just now I said the method, exactly same method you can apply. Next one, ethane nitrile to ethanol. Ethane nitrile to ethanol. So whenever RCN is given and you want to convert it into RCHO, whenever RCN given, or I will write all cases, whenever RCOCl acid halide, nitrile and ester given and you want to convert this into aldehyde, then you can give dival H followed by addition of water. For CN2 aldehyde, we can have one more method, SnCl2HCl followed by hydrolysis, Stephen's reaction. Any of these two methods can be used. So now what they are saying, ethane nitrile to ethanol. We can go for diol H followed by hydrolysis, or we can go for Stephen's reaction, means SnCl2HCl followed by hydrolysis. Okay, next one, allyl alcohol to propanol, allyl alcohol to propanol, allyl alcohol to propanol, simply PCCl. Next one, but2ene to ethanol, but2ene CH3 CH double bond CH3 to ethanol CH3CHO. How it is possible? If I want to break this carbon-carbon double bond of this alkene and I want to bind only one oxygen there, then I will go for ozonolysis, means O3, firstly treated with O3 followed by H2OZN. Ozonolysis. What ozonolysis is? O3 followed by H2OZN given, break carbon-carbon double bond of alkene, bind oxygen. So check that, this becomes CH3CHO, CH3CHO. Okay, next. Okay, write the structure of product formed there. What will happen? This is benzene, this is acid chloride, anhydrous AlCl3 given. Friedel-Crafts alkylation, Cl minus migrate towards AlCl3. This will generate electrophile C2H5 C plus double bond O. This electrophile bind to the benzene, means your first reaction product will be what? C double bond O C2H5. Second reaction, C6H5CH2CD given, means it is given like this, C6, so I am writing PH CH2CD CH2PH, this is given, and treated with CH3C double bond OCl. Cadmium is a metal, so metal is going to acquire plus charge, carbon will acquire minus, and it is common sense. Metal will acquire plus charge, so carbon will acquire minus charge. And in this case, this carbon is a plus. So this carbon minus attack on this, and Cl is leaving group, so will leave. What will form? You can check CH3 C double bond O, and this CH2PH bind there, CH2PH. This is your product. So how to find? By polarity only. Cadmium is metal, so metal is a plus, carbon is a minus. This minus attack on this carbon, Cl leave. Okay. Next one. This is given HgH2SO4. HgH2SO4 given, means consider this as H2OH plus. You can, to make reaction product, think about the reaction product easily, you can write water as H plus OH minus. This is only for understanding. Then how to find product? Markovnikov. This carbon, no hydrogen. This carbon, one hydrogen. So this carbon has less number of hydrogen. Now bind OH to this carbon by breaking one pi bond. So if I am breaking one pi bond and binding OH there, what I will get? CH3, C, OH, double bond, CH2. This is what? Enol will go for tautomerism. And by tautomerism, what will happen? Carbon-carbon double bond becomes single, and carbon-oxygen single bond become double. Double become single, single become double. So what you will get there? CH3, C double bond O, CH3. So here I am solving by Markovnikov, and then I am going for tautomerism. This is what? CrO2Cl2, solvent obviously carbon disulfide, followed by hydrolysis, etard reaction. What will happen? This CH3 group will become CHO. CH3 is converted into CHO, NO2 remains unaffected. So CH3 group becomes CHO by etard reaction. Okay, next one. Next problem. Okay, I explained you the concept of boiling point. So there is no need to discuss much. Alcohol boiling point more than aldehyde. Aldehyde more than ether and alkane. Ether alkane carbon count method, which I said you can solve 4 carbon up to 4 carbon of alkane. Ether is more, provided molar masses are comparable. This is also very important. This we discuss. Arrange the following compound in increasing order of boiling point. We discuss alcohol more than aldehyde, aldehyde more than ether and alkane. Alkane 3 carbon means ether is more. That's it. I said simple method for all boiling point cases as per our syllabus. Next problem. Okay. Next problem. Okay, this problem. Organic compound A with molecular formula C8. Okay, see, this type of question you can solve by eliminating the options. For example, what they are saying, red precipitate 2,4-DNP. Giving 2,4-DNP test means it is either aldehyde or ketone. DNP test positive means it is either aldehyde or ketone. Based on this, you can find this. Then they are saying then they are saying precipitate on heating with iodine in the presence of sodium hydroxide means giving positive iodoform. Positive iodoform means one side is CH3. One side is CH3. It is fixed. CH3CO is there, then only it can give positive iodoform test. What is the formula given? C8H8O. Out of C8H8O, count 2 carbons gone. 2 carbons gone. How many carbons left? 6 carbons. 1 oxygen gone. 1 oxygen gone, 2 carbon gone. 3 hydrogens also gone. So 8 minus 3, 5. C6H5 means another part is C6H5. Solved there. Don't think it is a very big problems, will take much time. If your fundamentals are strong. Sir, if pentane and diethyl ether is given, then which has more boiling point? Pentane means how many carbons? 5 carbon na yaar. 5 carbon na means alkane more than, pentane more than diethyl ether. You can check NCERT data. Okay, so DNP test given means aldehyde or ketone, and positive iodoform given means one side CH3. Now what formula given? C8H8O. C8H8O given. CH3CO. This part I took from positive iodoform. From this I took. So 2 carbons gone, minus 2 carbons, 6 carbons left. 3 hydrogens gone, minus 3, 6 hydrogens left. Sorry. C6H5. C6H5. 8 minus 3 is equal to 5. Your math is very strong. I know this. So 8 minus 3, how much? My math may not be strong. Yours is good. 8 minus 3 is a 5. So C6H5. This part is C6H5. That's it. Okay. So problem is big. But if you're knowing concept, it is very easy. Okay. Next problem. Arrange the following compounds in the increasing order of their reactivity. What is given? Ethanol given. Ethanol given. Ethanol. Propanol. Propanone. And butanone. In case of aldehyde ketones, generally aldehydes are more reactive. Why more reactive? Check here. This is chinna atom na yaar, will provide less hindrance. Ethyl, methyl. Who is big? Ethyl big. So in this case, both side big. Inside one very big, one moderately big. This side very small. Small groups are attached. Aldehyde more reactive. So 1, 2, 3, 4. 1, 2 aldehydes. 1, 2 aldehydes more reactive than 3, 4. Aldehydes are more reactive than ketones in general. Okay, aldehydes in general more reactive than ketone. Then how to compare 1, 2? Steric hindrance, this is more hindered, less reactive. So 1, 2, 2 more 2 less reactive. This side, both side methyl here, one side ethyl. Big group, more repulsion, less reactive. So your fourth is less reactive than 3. Okay, so I think you got the answer for this. Next one. Benzaldehyde, para-nitrotoluenaldehyde, para-nitrobenzaldehyde, and acetophenone. Benzaldehyde, para-toluenaldehyde, para position CH3. Para-nitrobenzaldehyde, para position nitro group, benzaldehyde, and acetophenone. So this is your ketone, and these are aldehydes. So we can say generally aldehydes are more reactive than ketones. Then how to find others? See here. This carbon is a plus, this carbon is plus. Who is attacking on plus? Obviously nucleophile. Minus will attack Nair. If more plus charge, if this carbon has more plus charge, nucleophile can attack more. Na? CH3 is giving, so decreasing plus charge. NO2 is taking, so increasing plus charge. More plus charge, nucleophile can attack more. Less plus charge, nucleophile can attack less. So out of these three, this is more reactive, then this, and then this. Clear or not? So very simple. First is steric hindrance more, reactivity of aldehyde ketone less, delta positive charge more, so attack of nucleophile more, so reactivity also more. Predict the following reactions product. What is given? This CO given, NH2 given. How to remove water? Oxygen of this and hydrogen of this. H2O minus H2O. Easy na. H2O. So by removing H2O, what you will get? The double bond NOH. Oxime is formed. Here also, this O and these two hydrogen. Remove H2O minus H2O. What will form? Double bond N. Then next is this NH, this NO2, and this NO2. This is 2,4-dinitrophenyl hydrazine. This is 2,4-dinitrophenyl hydrazone, which is colored, used for the identification of aldehyde or ketonic group. Next is, this is given. Now this is a very important. Now this is this is from, I can remove water from here as well as from here. How to find which hydrogen I have to select? So this hydrogen, this nitrogen is going for resonance with this CO, na? So this will not be selected because involved in resonance. Bijine resonance here. This lone pair is Bijine resonance. How it can go for the reaction? This nitrogen is a free saying I am available to react. So I will remove this oxygen and this hydrogen as water. So means this. So how to write product? This is R CH double bond CH. This nitrogen is binding with this carbon, so double bond N, then this NH, then this C double bond O, and then this NH2. So if this compound given, semi-carbazide given, then nitrogen involved in resonance will not go for the reaction. Nitrogen who is not involved in resonance will go for the reaction. Okay, next. This is given, simple method, same, oxygen and hydrogen, remove water. Sif base is formed. Okay. Next one. Next. Write chemical reactions to affect the following trans. That's why I explained just a few minutes back. Ki alcohol to acid, primary alcohol to acid possible by strong oxidizing agent. Benzyl alcohol to benzoic acid, same aldehyde to alcohol, strong oxidizing agent. 3-nitrobromobenzene to 3-bromo-nitrobenzoic acid. This is important. This is not discussed. Okay, so let's discuss number 3. What is given there? 3 nitrobromobenzene to 3 nitrobenzoic acid. Means basically I have to write I have to put COH group there. So what is the method there? Firstly, treat with magnesium in dry ether. Magnesium dry ether. This will make Grignard's reagent MgBr, and this is NO2. Treat this with dry ice, carbon dioxide. This Grignard polarity you are knowing. This magnesium plus carbon minus attack on this carbon, pi bond will break by this reaction and then followed by H plus. By this reaction what will happen? In the place of this carbon who will come C double bond. This is C double bond O. This become O minus bind with this H plus. Mean this part becomes C double bond OH and this remains unaffected. So means if you want to convert halobenzene into benzoic acid, firstly convert into Grignard, then treat with carbon dioxide followed by acidification. Simple. Okay, next one. 3-methyl acetophenone to benzene 1,4-dicarboxylic acid. Sorry, 4-methyl acetophenone to benzene 1,4-dicarboxylic acid. What is given to you? What is given to you? Acetophenone and 4-position methyl. What is the method? Strong you are knowing ketones are generally not going for oxidation, but they can be oxidized in the presence of strong oxidizing agent and heating. If a strong oxidizing agent heating taken, what will happen? This bond I cannot break, I will break this bond. So this part becomes COH and this CH3 also oxidize into COH. So what will form there? This CH3 oxidized becomes COH and this CO also oxidized become OH. Strong oxidizing agent like K2Cr2 7H+, H2CrO4, you can take any strong oxidizing agent with heating. Then what will happen? This bond will break, ketone bond will also break, this become acid and this CH3 will also oxidize. Okay. Cyclohexene to cyclohexane 1,6-dioic acid. What is given? Cyclohexene given. Cyclohexene given. And what I have to make? This compound. How I can make? For this also I will use a strong oxidizing agent and heating. Or they may give simply strong oxidizing agent also. Method, break this bond, oxygen, oxygen. Break this bond, oxygen, oxygen. So by this what will come? This becomes CHO and this also becomes CHO. Since a strong oxidizing agent is taken, this CHO will oxidize further and become carboxylic acid. Butanol to butanoic acid. Aldehyde to acid. Strong oxidizing agent. Even some mild oxidizing agent like tolerance reagent can also be taken. It is butanol aliphatic aldehyde, so Fehling solution can also be taken. So butanol to butanoic acid, this conversion is possible by strong oxidizing agent and some mild oxidizing agent. Some mild oxidizing agent like tolerance reagent and Fehling solution can also be used for this conversion. Then this is the answer for this explanation here. Now they're asking, how each of the following compound can be converted into benzoic acid. Just now I explained how to convert compounds into the benzoic acid. For example, ethyl benzene given. Ethyl benzene given. This is your ethyl benzene. If carbon attached to benzene is having minimum 1 alpha H present, then in the presence of a strong oxidizing agent and heating, this carbon will oxidize into COH. If basic medium taken, then carboxylate. So if carbon attached to benzene is having minimum 1 hydrogen or minimum 1 alpha H present, that can be converted to benzoic acid. Acetophenone I explained earlier. Bromobenzene to benzoic. Just now we discussed. Firstly, convert this into Grignard, then treat with dry ice, then acidify. Phenylethene, same method, this method. Okay. Then phenylethene can be oxidized with strong oxidizing agent. Next. Oh my God. Okay, this one last problem is there. Which acid each pair, so the expected stronger acid, acidic strength we have to find. Very easy concept. If functional groups same, if functional groups are same, then I can say minus I minus M increases acidic strength. This is plus I, CH3 plus I na, acidic strength decrease. Fluorine minus I, acidic strength increase. So second is more acidic. Here it is a fluorine minus I, here it is chlorine minus I. Both are minus I. Minus I of fluorine is more. So minus I of fluorine more. So increase in acidic strength, the presence of fluorine is also more. In this case, first is more acidic. Next case, this is COH group, CH2, CH2F, fluorine. Here also fluorine, but here fluorine attached at 1, 2, this is attached to this carbon. So what will happen? This is CH, CH2, okay, attached to fourth carbon. Attached to fourth carbon is attached to third carbon. Obviously, you are knowing inductive it is distance dependent. So here it is away from COH. So its minus I is less. So increase in acidic strength also less. Here its minus I is big. Increase in acidic strength is more. In this case, the second is more acidic. CF3, it is a minus I group. CH3 plus I and plus H group. And functional group is same. COH, COH. This is very important to observe first. Functional group. We are applying minus I minus M if functional group is the same. So same functional group minus I increases acidic strength, plus I plus H decreases acidic strength. So in this case, first is more acidic. Okay, so this is done. Okay, let me check anything left or no, nothing. No. Okay, Hypoindi. Next topic, last chapter of organic chemistry, amines. Where it is? This one. Yes, for inductive effect we are following DNP rule, distance, number, power. Firstly check distance, then number, and then power. More distance, less inductive effect. More distance, less inductive effect. Amines, very important chapter. Okay, first question is there. Classify the following amines as a primary, secondary, and tertiary amines. I will tell you one simple method. Firstly, I'll tell you the concept, then I will tell you simple method. Oh my God, 1 minute. If it is RNH2, it is a primary amine. If it is RNHR, it is secondary amine. And if it is R3N, it is a tertiary amine. What is the simplest identification? NH2 given primary, NH given secondary, N given tertiary. Simple. How to observe clear? NH2 primary, NH secondary, and tertiary. Now check. It is NH2. It is NH2. It is a primary. Directly attached to benzene, so primary aromatic amine. This is N. So it is a tertiary. And directly attached to benzene, so primary aromatic. Tertiary aromatic amine. See here, it is NH2 primary, and it is not benzene, so it is, I can say it is a primary aliphatic amine. This is NH, I can say it is secondary aliphatic amine. I think it is clear to you. How to identify? NH2 primary, NH secondary, and N tertiary. By this method, you can easily find primary, secondary, tertiary amines. Next question. Okay. Okay, so let's focus here. Next problem. Write structures of different isomeric amines corresponding to the molecular formula C4H11N. C4H11N. You have to find number of isomeric amines corresponding to this formula. How to find? Firstly, think about the primary. Firstly, think about the primary amines. Primary amines. Primary amine means what? NH2, na? NH2. So this side, how many carbons are there? C4. So 4 carbon, I can write 4 carbon chain like this, and in 4 carbon, another possibility is this. By 4 carbon, we have these two possibilities. Na? Now, I have to attach NH2 group there. So I can write 2 different symbols for this. So 2 possibility will come here, and for this, these 3 are identical, and this one is different. 2 symbols for this. So how many primary amines came? 2 plus 2, 4. Then I will go. Understood the method now? Okay. Then I will go for the secondary amine. Secondary amine means what? NH. Secondary amine means NH. Total carbon count 4. So first possibility, one side 3 carbon, other side 1 carbon. Next possibility, 2 carbon both side. Now, if it is a 3 carbon, how many different symbols you can draw? 2 different symbols. So for this condition, I will get 2 secondary amines. If it is a 2 carbon, both are identical, na? Here also same. So there is no second possibility. Only one possibility will be there. So how many secondary amines are coming? 3. And tertiary amines means N. How many carbons? 4. So one possibility, 1 carbon, and this is 2 carbon. 1 carbon, only one possibility. 1 carbon, only one possibility. 2 carbon, also only one possibility. Means single possibility there. There is no second possibility for the tertiary amine of this question. So how many amines came? 4 primary, 3 secondary, 1 tertiary. Total 8 amines came. Out of 8, 4 are primary, 3 are secondary, and 1 is tertiary. Very good question and very important. Write IUPAC name of all isomers. You can write what is the type of isomers, different pairs of them. Primary, secondary, tertiary amines are functional group isomers. Primary, secondary, and tertiary amines are functional group isomers. Next question. Reaction of ethanolic NH3 with C2H5Cl. What is given to you? C2H5Cl given. I am writing only carbons, ignoring hydrogen. Treated with ethanolic NH3. Ethanolic NH3. NH3 is reagent, ethanol is solvent. What will happen? Nitrogen contains lone pair. Attack on this carbon, remove Cl directly. You can directly get product. Why to waste time for this? Why to go for the actual mechanism? What is happening? Not required. Na? They are asking product. We are interested in product. Nitrogen is containing lone pairs. Nucleophile attack on carbon. Cl leave. It becomes NH2. Sir, why NH2? Arey, this Cl minus is coming out. When this Cl minus coming out, will take hydrogen from the NH3, na? So minus HCl. That's why it is NH2. But they are saying reaction of ethanolic NH3 with C2H5. They are not saying 1 mole or 2 mole or 3 mole. They are saying just write the reaction. So we have to think about all possibilities. Then this amine will react with another molecule of this ethyl group. This will attack on this. Cl will leave. So Cl leaves, Cl minus H plus leave as HCl. What will happen? This is carbon NH carbon. Then this react with another molecule. This nitrogen contains lone pair, attack on this Cl leave. So Cl minus and this one hydrogen coming out as HCl. What is formed? Carbon, nitrogen, carbon. And one more molecule of ethyl chloride can react. This nitrogen contains lone pair, Cl leave. But this time there is no hydrogen attached to nitrogen to leave as HCl. Then what will happen? This one carbon bind to this nitrogen. This become carbon. There also carbon. Here also carbon. Now nitrogen making 4 bonds of plus charge, and this Cl minus will neutralize this. So quaternary ammonium salt is formed. So very simple reaction there. NH3 attacks Cl leave, then this amine attacks Cl leave, then this amine attacks Cl leave, and then this amine attacks Cl leave. That's it. So you got primary amine, secondary amine, tertiary amine, as well as you got quaternary ammonium salt. Second question they are saying, ammonolysis of benzyl chloride and reaction of amine, so from 2 moles of CH3Cl. Now this time they are saying ammonolysis of benzyl chloride, this is your benzyl chloride, ammonolysis means treat with ammonia. What will happen? NH3 attack Cl leave, attack. What is formed there? pH CH2 NH2. Then they are saying 2 moles of CH3Cl. So 2 moles of CH3Cl. Firstly take 1 mole of this nitrogen attack on carbon Cl leave. So this Cl minus and this H removed as a Cl. What is formed? CH2 NH CH3. 1 more molecule of CH3Cl will come because they are saying 2 moles attack Cl leave. Cl minus H plus leave as HCl. What is formed? pH CH2N CH3. This is your product. So concept is very simple. N attack Cl leave. N attack Cl leave. That's it. Very easy method. Next, write the chemical reaction for the following conversions. What is given? What is given? CH3 CH2Cl given, and I want to convert this into CH3 CH2 CH2 NH2. Now check here. Left hand side I have 2 carbons and right side I have how many carbons? 3 carbons. I want to increase carbon count. 2 carbons in left and right side, 3 carbons. If you want to increase the carbon count, best possible reagent as per our syllabus is KCN. Treat with KCN. Ethanolic KCN can be taken. You can take ethanol as a solvent or you can take ethanol water also as a solvent. KCN, K plus Cn minus carbon attack, Cn minus attack Cl leave. What will form first? First this will give CH3 CH2 Cn. Cyanide or nitrile formed as a measure. Then this to this, how possible? See, this is a Cn. I want to this is Cn means what? Carbon triple bond nitrogen. In the place of carbon triple bond nitrogen, I want to write CH2 and H2 here. I have to bind hydrogen there. Reducing agent required. We can go for Sn plus HCl. We can go for sodium amalgam plus ethanol. We can go for H2, Ni, PD or PT. Even we can go for Li, LH4 reaction also. Any one of them can be taken to convert this Cn into CH2 and H2. Yes, sodium amalgam. It is NaHg ethanol. You can read from your NCRT. We can use NaHg plus ethanol. Okay, this is done. So first is done. Second also same method. Cl is given and you have to bind CH2 and H2 there. Cn and then reduction. Okay, what they use? H2 and I they use. Okay, you can use H2 and I PD. Okay, 1 minute. Yes. If you want to convert Cn into CH2 and H2, then you can use H2 and I PD. You can use sodium amalgam ethanol. You can use SNHCl. You can use LiLH4. Okay. Now, next question is based on Hoffman bromamide degradation. So I will tell you firstly reaction. Whenever we have R or pH, aliphatic or aromatic primary amide, and it is treated with Br2KOH, aqueous or alcoholic, or examiner may simply write KOBr, what will happen? This CO will be removed and NH2 bind with this R or pH. Means this CO part is removed, NH2 part bind with R or pH. So R or pH bind with this NH2, it has become R or pH NH2, and the CO part removed as K2CO3. So if I have n carbon atoms in amide, then amine is having one less carbon now, because one carbon gone. After knowing this, you can easily find the reactions. What they saying? Amide which can give propanamine. So propanamine, how many carbons? 3 carbons. Hoffman bromide, they are saying propanamine I want to prepare. It has 3 carbons, so amide must be having 4 carbons. Just now it is observed here na. If amide has n carbon, amine has 1 less carbon in Hoffman bromamide degradation reaction. So if it is amine of 3 carbons, I need amide of 4 carbons. Next, the amine produced by Hoffman degradation of benzamide. Benzamide means what? pH C double bond ONH2. Hoffman bromide KOBr. What I said in what will happen in Hoffman bromide degradation? CO going out, PHNH2 combine, it become PHNH2. So aniline is formed, or benzenamine is formed. Next one, propanamine. Propanamine containing 3 carbons. Okay, they are explaining it. Okay, that is discussed. Okay. How will you convert benzene into aniline? How will you convert benzene into aniline? This is benzene and I want to make it aniline. How I can make? Firstly, I will give nitrating mixture HNO3 plus H2SO4. So by this what will happen? This is going to become nitrobenzene, and this nitrobenzene can be converted into aniline. How it? This is nitrobenzene, NO2. Nitrobenzene, NO2. This nitrobenzene can be converted into aniline. How we can convert this? Answer is we can use H2PD. We can use FeSCl. We can use SnSCl. Out of these, FeSCl is a preferred method for this conversion. Okay. In this case, LiAlH4 cannot be used. This year's JEE Mains problem. LiAlH4 cannot be used for this conversion. Why it cannot be used? Because LiAlH4 is reacting differently. How reacting? Not required. Not in your syllabus. Only one thing required for nitrobenzene to aniline conversion. What we cannot use? LiAlH4 cannot be used. Why it cannot be used? Because it is reacting differently. Reacting, but reacting differently. How they are reacting? Not required. Next question. What they are saying? You have Cl, CH2, 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 Cl, and you want to prepare, you have to prepare this amine. Now observe, this alkyl halide has 4 carbons. This alkyl halide is having how many carbons? 4 carbons. But this amine is having 6 carbons. Means I need to increase the carbon here. And what I told, if you want to increase the carbon, best reagent as per our syllabus is CN. So firstly treat with KCN. Cl displaced by Cn, Cl displaced by Cn. So this becomes Cn. Carbon, 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 and Cn. Don't say, sir, it is Nc. Carbon is connected to this carbon. This you have to read from this side. It is Cn. Carbon is connected to carbon, not nitrogen. It is a Cn group. It is a nitrile group. This is also nitrile group. Then this to this conversion, we discuss now. H2PD, H2Ni, SnSCl. and sodium amalgam ethanol, any one of them can be used. For example, let's say I'm using H2Ni. Done. Okay, so this is very good question, excellent question. Basic strength of amines, two important informations. If they're asking basic strength of ethyl amine in aqueous medium, ethyl amines in aqueous medium, then it is a 2 degree more than 3 degree more than, means it is 231 and then NH3. And if they're asking basic strength of methyl amines in aqueous medium, then it is a 213 and then ammonia. 213 and then NH3, ammonia. If they're asking basic strength of ethyl amines in aqueous medium, if they're asking basic strength of ethyl amines in aqueous medium, then answer is 231 ammonia, means 2 degree, 3 degree, 1 degree, then NH3. And they're asking basic strength of methyl amines in aqueous medium, then answer is 213. And if they're asking basic strength in gas phase, then it is 3 degree more than 2 degree more than 1 degree, then ammonia. Is it clear or not? So this basic strength part is very important, and let's solve the problems. First question, arrange the following in the decreasing order of their basic strength. First is given C6H5NH2. C6H5NH2. Next is given ethyl amine, then ammonia. Now, let's say we are comparing aromatic amine and aliphatic amine. In case of aromatic amine, this pair of electron is a delocalized. Since it is a delocalized, its basic strength will be less. In case of aliphatic amine, it is localized, so its basic strength is going to be more. I can make it simple. Ki aliphatic amines are more basic than aromatic amines. Basic strength, this is aromatic amine and this is aliphatic amine. Aliphatic amines are more basic than aromatic amines. Yes, aromatic amines are less basic. That's the same, Nayar. Same. Okay. So now, based on this, what we can say? This is your aromatic amine. And these two are aliphatic amine. So it is obvious. Let's say I'm writing 1, 2, 3, and 4. So 2 and 3, they are aliphatic amines. So 2 and 3 more basic than aromatic amine, means 1. And ammonia is present between both of them. NH3 is present between aliphatic and aromatic. NH3 is present between aliphatic and aromatic. So 2 and 3, these two are aliphatic amines. And 1 is your aromatic amine, and ammonia is present between them. Now, how to find these two? Ethyl, for ethyl, what we discussed, number is a 2, 3, 1. So 2 degree is more basic than 1. So 3 is more basic than 2. That's it. Okay. So next question. So this is, I think, clear to you. Next one. Next. Okay. Okay. Arrange the following in the order of their basic strength. Same concept came. Ethyl amine, benzyl amine, diethyl amine. Let's say I'm writing A, B, C, D, E. In this case, A, D, E, they are aliphatic amines. So A, D, E, they are more basic. Ammonia is present between aliphatic aromatic, and your B is aromatic amine. Aliphatic amine, ammonia, aromatic amine. Now A is ethyl, your D is this benzyl, and this E is diethyl. So now diethyl and ethyl. What is the number for ethyl amines? 2 degree, more than 3 degree, more than 1 degree, and then NH3, 2, 3, 1. So 2 degree more than 1 degree. So means E is more than A. And this case, pH is minus, I will decrease as basic strength. So after that it is a D, and then NH3, and then it is a B. Okay. So this is the answer. Likewise, you can solve. Next is direct question here. Direct question. Ethyl, and then aromatic. So ethyl is aliphatic. These three are more basic than this. And this how to find a 2 degree more than 3 degree more than 1 degree. Next also same problem. You can easily find it. Complete the following acid-base reaction. Now, if you have RNH2 and treated with HCl, what will happen? H plus Cl minus, lone pair is binding with H plus. What become? This become RNH3 plus and Cl minus. This primary ammonium salt is formed, which is soluble in water. If this is given R3 N is treated with HCl, lone pair bind with this H plus. Lone pair means base. Lone pair means base. This is lone pair means base. Base bind with H plus. So what is giving? RNH plus Cl, quaternary ammonium salt form. Examiner may ask out of first second who will react more, who will react faster. So this is more basic now. This will react faster because 3 plus I is increasing the basic strength. Okay, so acid-base, right reaction of final alkylation product of aniline with excess of methyl iodide in the presence of sodium carbonate solution. What they are saying? Write the final alkylation product of aniline with excess of methyl iodide. Just previously only we discussed attack, then Cl leave. Here it is. Iodine will leave. We discussed this problem earlier only. Then next. Write the chemical reaction of aniline with benzoyl chloride. Okay. Write the name of the product obtained. What they are saying? Write the chemical reaction of aniline. Aniline. This is your aniline molecule. Benzoyl written. Benzoyl. See, if they are saying benzyl, let's say they are saying benzyl chloride. Benzyl chloride, it is a PHCH2Cl. If I replace this hydrogen by hydrocarbon, then also benzyl. And they're saying benzoyl, then it is a PHCOCl. Benzoyl chloride. Now in this question, what they are saying? Benzoyl. This is your benzoyl chloride. Remaining story you are knowing. Lone pair attack on this carbon, Cl leave. So Cl minus NH plus remove as HCl. What will form? PHC double bond O. NHPH. This reaction, binding of benzoyl group, is known as a benzoylation reaction. It is known as benzoylation reaction. Okay. So write the chemical reaction of aniline with benzoyl chloride. Write the name of product. Product you can say N-phenyl benzenamide. Okay. Next. Write structure of different isomer. Now they are asking now this time C3N. C4N I explained to you. C4N, 8 amines, 4 primary, 3 secondary and 1 tertiary. In same way you can solve C3H9N. Same concept, even it is easier than that here. Okay. Okay. And primary amines, when primary amine, now they are asking who will liberate nitrogen gas. So when primary amine is reacting with HNO2, it is making RN2 plus Cl minus, which is highly unstable, immediately decomposed and giving alcohol and nitrogen gas evolved. So primary amines are are giving alcohol and evolving nitrogen gas when treated with HNO2. Next. Okay. Question is, how will you convert 4-nitrotoluene into benzoic acid? 4-nitrotoluene into 2-bromobenzoic acid. 2-bromobenzoic acid. How this conversion is possible? So first of all, I will treat this with Br2 in the presence of some Lewis acid like FeBr3. This will generate electrophile Br plus. NO2 is meta-directing and this is ortho-para-directing. Ortho by reacting and activating. So this is giving direction for this ortho, this para. Para not available for the reaction because NO2 already bonded there. So this Br plus bind at this ortho position. So electrophilic substitution reaction is giving CH3Br and this is NO2, first product obtained. Then only one thing required, remove this NO2 group. Very important concept. If you want to remove this NO2 group, first of all, convert this into NH2. How I can convert this into NH2? So we discussed in H2PD, FeScl, SnScl. I am writing best one FeScl. This become NH2. Then convert this NH2 into disonium ion. How to convert into disonium ion? This is a Br. How to convert into disonium ion N2 plus Cl minus? Answer is by giving HNO2 temperature 0 to 5 degrees Celsius. Aromatic primary amines can be converted into disonium salt by giving HNO2. HNO2 given in the form of NaO2HCl. If it is aliphatic primary amine, its disonium is highly unstable and decompose and give alcohol. Now this to this, how it is possible? This conversion means I want to remove this N2 and I want to bind hydrogen there. It is possible by ethanol or by H3PO2. Possible by ethanol or by H3PO2. So if you want to remove disonium, this is disonium ion N2 plus. If you want to remove disonium ion, this N2 plus you want to remove as nitrogen gas and want to bind hydrogen there, then ethanol or H3PO2 can be used. Yes, HNO2 coming from NaNO2 plus HCl. Reaction performed in ice bath cold conditions. Okay, so this conversion is, I think, clear to you. Next is 3-methylaniline to nitrotoluene. 3-methylaniline. This is aniline molecule. 3 position is methyl. And what they are saying, I have to bind NO2 group in the place of this NH2. How it is possible? How this conversion is possible? How this conversion is possible? First of all, convert this into disonium. So I am telling only this part. Convert this into disonium ion. How can we convert it? HNO2 0 to 5. Then treat this with HBF4. In case of HBF4, Cl minus replaced by BF4 minus, it become N2 plus BF4 minus. And then this to this conversion possible by heating this compound with NaNO2 in the presence of copper. Okay or not? So this conversion is a very easy. What exactly I am doing? We have this PHNO2 converted into PHNH2. How converted? Fe plus HCl. This also already aniline given. PHNO2, PHNH2. It is converted into PHN2 plus Cl minus. How it is converted? By giving HNO2, means NaNO2 plus HCl 0 to 5 degrees Celsius temperature. Then this is treated with HBF4. What happens? Cl minus displaced by BF4 minus, this become PHN2 plus BF4 minus. Then this PHN2 plus BF4 minus is treated with NaNO2. Heating is done in the presence of copper. Then N2 will come out and NO2 bind there. It become PHNO2. And if it is directly heated, then it become PHF. Okay, so this conversion is they are using in this question. Okay, so this chapter also done. So organic chemistry part is completed. Let's focus on the inorganic chemistry part. So first I will take coordination chemistry. Where it is? Coordination chemistry. First problem. What is that they are saying? On the basis of following observations made with aqueous solution, assigns secondary valency to the metal in the following compound. Secondary valency means what? Number of donor atoms directly connected to the central metal ion. How to find? What they are saying? Mole of AgCl precipitated 2. So 2 mole precipitated. It is given PdCl2NH32. So its formula will be something like this: the PD. If this 2 moles of Cl precipitated, means 2 moles of Cl present outside now. So it is a PdCl2 only. Both chlorines present outside, and 4 ammonia left. They are present inside. So how many donor atoms are connected to palladium? 4. So its secondary valency is 4. This case, what they are saying? How many chlorine atoms are present outside? 2. So how to write the formula? NiCl2 6H2O given. Ni is there inside the coordination sphere. Both chlorines are present outside because they are saying 2 chlorine get precipitated. So obviously coordination 6 is satisfied by the water. It is H2O6. So 6 ligands are bonded with this nickel. So secondary valency for this is 6. Next one. PtCl4 2HCl. What are they saying? No chlorine, no precipitation of AgCl, means these 4 plus these 2Cl, all 6, these 4 and these 2, all 6 are present inside the coordination sphere, means it is a PtCl6. PtCl6, platinum plus 4 Cl minus 6, so minus 2 charge na. So it is like this. Now in this case, how many ligands connected to this chlorine? 6 to this platinum. So secondary valency becomes 6. Next problem. COCl3. What they are saying? 1 chlorine is precipitated. Means out of 3 chlorines, 1 is outside. So 1 chlorine I am writing outside. Total chlorine count how many? 3. Out of 3, 1 outside. How many left? 2. So 2 chlorines present inside. What left? 4 NH3 left, and coordination number is 6. So NH3 4. So 2 plus 4 6, secondary valency 6. Similar manner you can solve next also. In this case 0 Cl means Pt, all chlorines present inside only. So it will be PtCl2 NH3 2, and this is complex. So coordination number is 4, so secondary valency also 4. And you must know platinum plus 4, coordination number 6, platinum plus 2, coordination number 4. Next question. Okay, next problem. Write the formula following coordination compounds. What is given? Tetraamine. If they are writing AMMINE, it is NH3. Okay, so tetraamine aquachlorido means and cobalt. So cobalt is present. How many amines they are saying? 4 amines. NH3 4. Aqua means H2O. They are not saying di or tri means only one H2O. And chlorido, they are only saying chloride means only 1 chlorine. Third, so how to satisfy the oxidation state? Check here. If I am taking this is 0 charge, and they are saying cobalt third. So if cobalt is a plus 3, this is 0, this is minus 1. So this charge on complex is plus 2 now. So it is written chloride here, means two chloride ions will come to satisfy this +2 charge. So this is the formula: CO NH3 4 H2Cl, and outside the coordination sphere 2 chlorine. Next one, potassium tetrahydroxidozincate second. Tetrahydroxido. Potassium, okay, I'm writing K. After this, I will balance it. Tetrahydroxido zinc. So zinc and tetrahydroxido means 4 hydroxy groups there. Zinc is a +2 written there. OH is -1, so -1 into 4 -4. So +2 -4. This is -2 na. So 2 potassium required to neutralize the charge. So it is K2ZnOH4. Next, potassium trioxylato aluminium 3. Aluminium, how many oxalato they are saying? How many oxalato they are saying? Tri. Oxalato means what? C2O4, 2 minus 3. Then we have to think about the potassium. Aluminium plus 3. 1 oxalate minus 2, so 3 minus 6. So charge on complex minus 3. So how many potassium required? 3. So K3. Similarly, you can solve next also. Next is written, write the IUPAC name of the following coordination compounds. What is the rule? Write name of ligands followed by metal ion. So it is amine A, chlorido C, and nitrito NN. So alphabetically A coming first. So I will say diamine chlorido nitrito N. Charge on complex 0, so I will directly use the platinum name, platinum, and oxidation state second. Okay. Next one. Now in this case, K is written before coordination means plus. So potassium, and this is what? 3 oxalates, so trioxylato chromium, and oxidation state third. So in this case, chromate, because it is anionic complex. If complex is anionic, then metal is named like 8, chromate, cobaltate, nickelate, platinate, like that. If it is a 0 or plus complex, then we are saying chromium, iron, platinum, like that. Okay. So in this case, you can easily answer it is an anionic complex of chromate. In this case, this example is very important. Why very important? Because outside we have mercury, and mercury has variable oxidation states. Here it is Hg+1. So I will say mercury first. Here I have to mention the oxidation state of Hg also. Here I am not writing. Here I am writing only potassium, because potassium is only one oxidation state. +1. Hg has variable oxidation states. That's why it is important to write the oxidation state of mercury also in this case. So this example is very important. Why very important? Because outside is Hg, and Hg has variable oxidation state, and that's what you can check there. They're writing mercury first. They're writing oxidation state of mercury also. Remaining you are knowing 4 NaCN minus, so tetrathiocyaneto, or then cobalt is minus complex, so I can say cobaltate. Okay. Now in this case, sulfur connected to cobalt, so I have to say tetrathiocyaneto S. Is it clear or not? Okay. So I think it is clear to you. So it is mercury first, tetrathiocyaneto S, cobaltate third. Here, what is important? I have to write oxidation of mercury also, because it has variable oxidation states. Next problem. Write the formula, and this already discussed now how to write the names and everything. So why to waste time for this? Focus on the next topic. Okay. Why geometrical isomerism not possible in tetrahedral complex? Okay, let's say we have tetrahedral compound. Tetrahedral complex taken like this, and other I am taking is square planar. Coordination number 4, 2 geometries are possible. In case of tetrahedral, a relative distance between this and this and this and this all are same. Here this distance is more than this distance. So in a square planar, aerial distances are not same. That's why here GI is possible. In tetrahedral, aerial distances are same. That's why GI not possible. So why geometrical isomerism not possible in tetrahedral complex? Having two different type of unit like reason tetrahedral complex do not show geometrical isomerism because relative position of unit ligands attached to the central metal atom are same. What I said, in tetrahedral areal distances are same, that's why it is not undergoing for geometrical isomerism, but square planar can go depending on the other conditions are followed. Or written, draw the geometrical isomers of Fe NH3 twice, it is NH3 4, it is NH3 4, NH3 4, sorry, CN4 written, okay, NH3 twice CN4, NH3 twice CN4, so it is Ma2B4 type of complex, na? Ma2B4 type of complex. So A2, focus on A2. You can write both A at 90 degree cis form. Second possibility, you can write both A at 180 degree and others written like this. So both A 180 trans and both A 90 degree cis. So two geometrical isomers will come for Ma2B4 type of compounds. Next, out of following coordination entities, which is a chiral? So now let's say this compound given CrCl2OX2, this compound given. So now in this case I can write, focus on Cl2, I can write chlorine like this, Cl like this, oxalate. One possibility I can write at 180 degree trans. Second possibility, I can write both chlorine in cis position like this. This is your cis isomer and this is your trans isomer. This trans isomer is optically inactive. In this case, bidentate are present same side is optically active. Means its mirror image will be counted in stereoisomers. So if this compound given, they are asking how many geometrical isomers, answer is 2, cis and trans. And how many stereoisomers? 3, cis, trans and mirror image of cis. And if they are asking which isomer of this compound is optically active, answer is a cis. Is it clear or not? So this is a very important question. Examiner may ask directly from this point, and in isomerism part this question is very important. Next one, indicate the type of isomerism exhibited by the following compounds. Draw the structure. Just now I explained CrH2O2 and oxalate 2 given. Just now I said for this I will be having two forms, cis and trans. Out of cis and trans, cis form will be optically active and this mirror image will be counted. The stereoisomer count 3 and geometrical isomer count 2. If second compound given COEN thrice given, so for COEN thrice, ethylene diamine, bidentate ligand taken. In this case, you can check it is symmetrical bidentate, no possibility of GI, but this is optically active. So in this case, its mirror image will come for optical isomerism. So GI not possible, but optical isomerism possible. So two optical isomers will come, or stereoisomer count will also be 2. No GI, but 2 optical isomers. What is the identification? Bidentate present same side, na? Directly say optical isomerism is observed or it is optically active. Simple method. Next one. Give evidence that CONH35Cl. Okay. What is given there? They are saying give evidence for this. We have this compound CONH35Cl and outside SO4. What is given there? CONH35Cl and outside it is SO4. Second possibility given CONH35SO4 and outside Cl given. Obviously in both cases ions are different. First case, if I dissolve in water, I will get sulfate ion and this cation complex ion. Here I will get chloride ion and this complex ion. So ions are different. They are ionization isomers. Now, in this case, what is the experimental evidence? This is having sulfate ion. So if it is treated with barium chloride, it will give precipitate of barium sulfate. In this case, this has a Cl minus outside. So if it is treated with aqueous solution of AgNO3, this give white precipitate of AgCl. So if AgCl precipitate coming means Cl is outside the coordination sphere. If precipitate of barium sulfate coming when treated with barium chloride means sulfate ion is present outside. Okay, so this is a very important question. Experimental evidence is precipitate in this example. Next one, the spin only magnetic moment of this is given. Predict the geometry of the complex. What they are saying? Magnetic moment is 5.9. Magnetic moment 5 means unpaired electron count 5 na. Magnetic moment is 5.9 means unpaired electron count is 5. Now it is a manganese 2 plus. Manganese 2 plus. So manganese is 3d 5 4s2. So manganese 2 plus is 4s electron gone. So this is a 3d 5 4s0 4p0 4d0. Now what is given here? Magnetic moment is a 5.9 means unpaired electron count 5. So 5 unpaired electrons remains if I am writing configuration in this form. It is a d5 3d5. If this is written, then I have 5 unpaired electrons. Means in this case 4s and 4p orbitals are used for the hybridization. It is a coordination of 4. So these 4 are used for hybridization. Br minus giving lone pair in these 4 orbitals. So hybridization become sp3 and so geometry become tetrahedral. So in this question, magnetic moment given, so unpaired electron count 5. That is possible only if it is existing as it is in the form of 3d5. No back pairing, nothing. Then it will go for this case and hybridization become sp3, geometry become tetrahedral. Next problem. Okay, explain on the basis of VBT. Okay, if I have NiCN4, NiCN4 2 minus, this is Ni2 plus, nickel 2 plus, means 3d8 configuration. So 3d8 4s0 4p0 4d0. Now they are saying explain of its valence bond 3 NiCN4 ion with a square planar geometry is a diamagnetic. So now 3d8 1 2 3 4 4s, then 4p and then 4d. This is the condition. This is 3d, this is a 4s, this is a 4p and this is a 4d. What condition given there? Is square planar complex means dsp2 hybridization na? Is square planar means dsp2 hybridization. So d, 1 d orbital, 1 s orbital and 2 p orbitals. dsp2 hybridization is done. Then only it will become square planar na? Then it is a d8. How to fill? Now these 4 orbitals are available to fill these 8 electrons. How to fill? 1 2 3 4 5 6 7 8. Any unpaired present? No. No unpaired electrons, so it become diamagnetic, magnetic moment 0. If it is NiCl4, then what will happen? NiCl4, it is tetrahedral. If it is a tetrahedral, then this is 3d, this is a 4s and this is a 4p. I am explaining second complex. Tetrahedral, so hybridization will be sp3 na? sp3. So these 5 d orbitals are available and it is d5. So how to fill? d8. 1 2 3 4 5 6 7 8. I have 2 unpaired electrons. It become paramagnetic. So concept is very simple. Next one, NiCl4 is paramagnetic. Why? NiCO4 is diamagnetic. NiCl4, just now I explained NiCO4. In case of NiCO4, if possible, directly memorize, it is sp3 hybrid, tetrahedral, diamagnetic. Very important example. NiCO4, sp3 hybrid, tetrahedral, diamagnetic. FeH2O6 is strongly paramagnetic, whereas FeCN6 is weakly paramagnetic. Explain. So it is given FeH2O6 3 plus given, H2O is a WFL, weak field ligand. So what will happen? Fe is given here. It is Fe, you are knowing atomic number of Fe is 26, means 3d6 4s2, but it is Fe3 plus. It is Fe3 plus, means 2 electrons of S and 1 electron of D gone. This is 3d5. Now it is a WFL. So how to fill electrons? 1, 2, 3, 4, 5. WFL. Na? So I will fill electrons like this. So I have 3 unpaired in T2G and 2 in EG. Means the total unpaired electron count is a 5. Come to the second case. Second case, what is given? CN. CN is SFL. Second is given to you FeCN. FeCN 6 3 minus. Here also it is Fe3 plus. It is Fe3 plus. It is Fe3 plus. Means here also it is a 3D5. Now in this case, this is a T2G level and this is your EG level. This is your SFL. So back pairing will happen and then 1, 2, 3, 4, 5. I am feeling like this. I have only 1 unpaired. This has 1 unpaired. This has 1 unpaired and this has a 5 unpaired. So both are paramagnetic. This has a 5 unpaired. Both are paramagnetic. But a 5 unpaired is strongly paramagnetic and one unpaired is weakly paramagnetic. They are not saying paradi. What they are saying? Both are paramagnetic. This is a strongly paramagnetic and this is a weakly paramagnetic. Reason very simple. This has a WFL. Back pairing will not happen. Yes. Cn minus is SFL. That's what it is. Cn minus is a strong field ligand. Cn minus is a strong field ligand. Yes. The answer is very simple. Okay, next. Explain CONH3 plus is inner orbital complex, whereas, okay, I will tell you one simple method. If you have D8, D9, D10 configuration for coordination number 6, whether you take SFL or WFL, in all cases, hybridization is going to be sp3d. This is for 3D, 3D8, 3D9, 3D10. You take any case, 3D8, 3D9, 3D10, take SFL or WFL, hybridization is going to be, sp3d2. sp3d2. Is it clear or not? In case of D8, D9, D10, hybridization will be sp3d2, whether it is SFL or WFL. Okay. Next one. So based on this, you can solve problem number 9.8. Predict the number of electrons in square planar PTCN2 minus. I explain NiCN4 2 minus in same manner PTCN4 2 minus can be solved because platinum belongs to the same group of nickel. Okay. Hexa-aqua-manganese ion contains 5 unpaired electrons while hexacyanide contains 1 unpaired electron. Same as what we discussed for 9.7. 9.7 Fe3 plus D5. Here 10.9.10 manganese 2 plus D5. Remaining constant exactly same. SFL, WFL, how to fill electrons. Just now we discussed what we discussed in 9.7. Same is for 9.10. Then. Okay, so this is about the coordination chemistry. This is about the coordination chemistry. In coordination chemistry, memorize spectrochemical series. This is very important. And if you know in this spectrochemical series, you can solve so many questions like if delta value more, then absorbed energy more, frequency absorbed more, wave number absorbed more, and wavelength absorbed less. Because you know E is equal to Hc by lambda. If E more, lambda less. So spectrochemical series is very important. If you're knowing a spectrochemical series, you must know one thing, that more delta value, more absorbed energy, more frequency, more wave number, but less wavelength. Energy and wavelength, they are reciprocal. But this discussion is for absorbed. Okay, this is very important concept here. Then this is okay. This is okay. No problem. Okay. In metal carbonyl, 2 points are very important. That this one, CO2, CO8 and Mn2, they are making metal bond. Here you can check cobalt bond is there. Here manganese bond is there. So examiner may ask which metal carbonyl is a dinuclear. Which metal carbonyl is a dinuclear? Which metal carbonyl is a dinuclear? You can answer in this case only one central metal mononuclear, 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 two metals dinuclear, two metals dinuclear. So these two metal carbons are dinuclear, they are having metal-metal bond. This is also very important in coordination chemistry. Okay, so let's move to the next topic, that is a DNF block. This digital board get tired. I'm not tired. Are you tired? Digital board is getting tired. I'm not. See what this is doing? Dancing. Are you tired? No, sir. No, sir. Datta is saying yes. Sarup, no. No. Paul, no. What is this, Pavitra? What is this? Okay. Okay, so DNF block. Very important topic, very important chapter. On what ground you may say scandium is a transition element but not zinc? See, if I'm writing a scandium, a topic number 21, it is a 3D1,4S2. So it has one unpaired electron in ground state, or it has incomplete D configuration in ground state. That is where it is transition. Concept is very simple. Those elements who are having incomplete N-1 D configuration either in ground state or in its stable oxidation state or common oxidation state, they are transition elements. Incomplete D configuration required either in ground state or in stable or common oxidation state. For example, I am taking zinc. Zinc is a 3D10,4S2, and if I am taking its common oxidation Zn2+, this is 3D10. In both cases, in ground state as well as in stable oxidation state, this is having fully filled D configuration or incomplete D configuration not present. That's why it is not a transition element. So examiner, if you are asking why zinc is not a transition element, you can answer, or zinc, cadmium, mercury, group 12 element, they are not transition elements because they don't have incomplete D configuration in their ground state as well as in their stable or common oxidation state. Then next, silver atom has completely filled D configuration. Okay, now they are asking silver is having 4D10 configuration. Silver to you are knowing na yaar. Silver is having 4D10 configuration. Then why it is silver atom has completely filled D configuration in its ground state? Then how you can say it is a transition element? I said na. What is the condition to become transition element? Either have incomplete D configuration either in ground state or in stable oxidation state or common oxidation state or both. I'll tell you one interesting example. Copper, because you are more familiar with this one. 3D10 4S1. If I take copper plus 1, it is a 3D10. But if I take copper plus 2, this will be 3D9. So copper plus 2 has incomplete D configuration. That's why it is transition element. Same justification you can give for silver also. So you can say its common oxidation state has incomplete D configuration. That's why it is a transition element. Next one. Why do transition element is high enthalpy of atomization? Why do the transition element exhibit high enthalpy of atomization? What is enthalpy of atomization for the metals? If I ignore mercury, most of the metals are solid. If I ignore mercury, all metals are solid. Metal solid converted into metal gas. This enthalpy of sublimation is called enthalpy of atomization. Why they have high enthalpy of atomization? Simple layer. Metal-metal interaction is strong. If metal-metal interaction is strong, they have a strong interaction, then their separation or converting them into gas is requiring more amount of heat or energy. That's why their enthalpy of atomization is high. Why they are having strong interaction? Because most of them are having unpaired electrons. Unpaired electrons will increase the interaction between metal-metal, and if interaction is strong, there more amount of heat is required, or large amount of heat is required to convert them into gas. So obviously their enthalpy of atomization is going to be high. Next question. In the series scandium and zinc, enthalpy of atomization is lowest. Okay, so now why it is lowest for zinc? In case of zinc, configuration is 3d10 4s2. Is there any unpaired electron? No, there is no unpaired electron. So interaction between two zinc atoms is very weak. It has a weak interaction. Why weak interaction? Because there is no unpaired electron. Unpaired electron count is 0 for the zinc. Because of weak interaction, its enthalpy of atomization as well as its melting point is extremely low. Okay, so I think you got the answer for this question. Next one. Next one. Name the transition element which does not exhibit the variable oxidation state. So check here. This is the table for the oxidation state. Here you can check. Scandium is having only one oxidation state. It is not having variable oxidation state. They are having multiple oxidation states. So they are having variable oxidation state. And zinc is not a transition element. So, and if they are asking who is having maximum number of oxidation states, then answer is manganese. You can check. Manganese has a 2 to 7. Maximum variations of oxidation states are observed in case of manganese, and no variation observed for scandium and zinc. And as per that question, answer will be scandium. Okay, so this is all, I think, very easy to understand. Then next, which of the 3D series of the transition metal exhibit the largest number of oxidation state and why? We discussed that's what we discussed. Manganese has maximum number of oxidation states. Reason, less energy difference there, so it can remove multiple number of electrons. Means it is configuration is what? 3d 5 4s2, and difference of energy gap is less between 4s and 3d, so all possibilities are there. Means remove 2 electrons of 4s, plus 2 will come, remove next electron of d, plus 3, likewise remove all electrons, it become plus 7. Question number, okay, now we have to discuss one more point. If we are observing plus 3, metal plus 3 plus 2 reduction potential, then titanium, vanadium, chromium, TV car, in these cases it is a negative, and next 3 after chromium will come manganese, iron and cobalt, these cases it is a positive. So if I am observing plus 3 plus 2 reduction potential, standard reduction potential, then for TV car it is a negative, and for next 3 it is a positive. Means in these cases plus 2 is more useful than plus 3, because positive na, and I am studying from 3 to 2. So in these cases plus 2 more useful than plus 3, and these cases plus 3 more useful than plus 2. So 3 to 2 conversion is reduction, means acting as oxidizing agent, and this plus 2 is acting as reducing agent. Okay, so this very simple concept, plus 3 plus 2 reduction potential, TV car negative, and next 3 are positive. Positive means what? 3 to 2 conversion is spontaneous. 3 to conversion is spontaneous, means going for reduction, acting as oxidizing agent. Simple. Okay, so now based on this you can easily find answer for this. Chromium plus 2 reducing agent, manganese 3 plus is oxidizing agent. What I said, titanium, vanadium, chromium. So chromium they have taken, manganese, iron and cobalt. This case 3 to 2 SRP, 3 to plus SRP is a positive. Means if I am taking manganese 3 plus, that can be converted into manganese 2 plus. Means it is going for reduction, so acting as oxidizing agent. While this case it is a negative, means chromium plus 2 to chromium plus 3 conversion spontaneous, so this is acting as reducing agent. Okay, this can be explained by the electronic configuration. Next and very important, if you are observing plus 2 zero reduction potential from from titanium to zinc, you will find for copper this is a positive, others are negative. So plus 2 reduction potential, and you are knowing from electrochemical series also, copper HAPA it is having positive SRP. So copper 2 plus, copper SRP is positive. SRP is positive. They are asking why. They are asking why. So answer is very simple. If enthalpy of atomization is high and hydration enthalpy is low, then sufficient amount of energy is not released, and this copper 2 plus copper become positive. Means basically when I am converting copper into copper 2 plus, because of this problem, this process become non-spontaneous, so this opposite process becomes spontaneous and it become positive. So I think this is also clear to you. So answer is very simple, and it is a very important question here. Why SRP for copper 2 plus copper is positive? You can answer due to high enthalpy of atomization and low hydration enthalpy. So hydration enthalpy is not able to compensate the atomization enthalpy. Next. How would you account the irregular variation in ionization enthalpies in the first series of transition element? See, if they are asking in case of 3D series, ionization enthalpy trend regular or irregular, answer is irregular. If they are asking why irregular, so because in case of 3D, ionization enthalpy depends on multiple factors like Z effective, means effective nuclear charge, exchange energy and shielding effect. Since it is dependent on multiple factors, it become irregular. Sometime exchange energy will dominate, sometime shielding will dominate. Z effective is saying कि left to right, Z effective increases, so ionization enthalpy increases. But in some cases, an exchange energy will dominate, change the trend. Likewise, shielding can also affect the ionization enthalpy. So if someone is asking in case of D block elements on 3D series, why ionization enthalpy trends are irregular, you can simply answer they are dependent on the multiple factors like effective nuclear charge, exchange energy, shielding. Okay or not? And they are having, for first ionization enthalpy, they are having very small difference between the ionization enthalpies of successive members. So because of very small difference also, large variation is created. Okay. Then next one. Next question is very important. Here you can observe, for when I am moving from vanadium to copper, just now we discussed copper has positive SRP. Positive SRP can be explained by high enthalpy of atomization and low hydration enthalpy. But other than this, observe here vanadium is large negative, manganese is also large negative. So you can easily understand how I can explain this thing. Positive explained by high enthalpy of atomization, so negative explained by low enthalpy of atomization. Clear or not? So, and low ionization enthalpy also. So what they are saying, plus 2 are not regular, which can be explained from the irregular ionization enthalpy and also the sublimation enthalpy, which are relatively much less for manganese. What I said, if you are saying positive SRP is due to high enthalpy of atomization and low hydration, then negative because of what? Opposite na yaar. Common sense. So you can say this manganese is low because of relatively less value of enthalpy of atomization or sublimation. Next one, this we discuss why manganese 3+ to manganese 2+ convert spontaneous. We discuss TB car 3 to 2 SRP negative and next 3 to 2 SRP positive. Based on this you can find oxidation reduction. Why is the highest oxidation state of metal exhibit its oxide? Okay, in case of highest oxidation state is mainly stabilized by oxides and fluorides. And out of oxide fluoride, oxide has more stabilization than fluoride, because oxygen can make double bond and fluoride can make single bond. So oxygen is able to make double bond, so steric crowding or steric repulsion in case of oxygen is going to be less. So highest oxidation state is stabilized by oxides and fluorides, and out of oxide fluoride it is more stabilized by oxides, because oxygen can form double bond and fluorine can form only single bond. Next one, calculate the magnetic moment of bivalent ion in aqueous solution, atomic number 25. Atomic number 25, so configuration will be 3d5,4s2. Bivalent saying, so 4s electron gone, become 3d5. Aqueous medium they are saying means WFL. So how to fill electrons? How to fill electrons? T2G, T2G, 1, 2, 3, 4, 5. How many electrons present? 5. So magnetic moment, spin only magnetic moment will be what? Mu is equal to 5 plus 2. So 5.9 will come. Is it clear or not? Next one. Calculate the spin, same method what I said. In this case they are saying D7, 27 is written. So it is D7, 3d7, 4s2. 3d7, 4s2. Water aqueous, so WFL, how to fill electrons? 1, 2, 3, 4, 5, 6, 7. How many electrons present? 3. You can calculate the magnetic moment. Next one, next. What meant by the disproportionation of oxidation state? This is discussed in redox. Same element going for oxidation as well as reduction is called disproportionation. Next and a very important question. If they are asking in aqueous medium out of copper 2+ and copper +1 and copper 2+, who is more stable? In aqueous medium, stability of copper 2+ is more. In aqueous medium, copper 2+ is more stable. Why? Because hydration enthalpy of copper 2+ is more. Now you will say, sir, in previous case, when you explain copper 2+ to copper 0, you said its SRP is positive because it has high enthalpy of atomization and low hydration enthalpy. Now here you are saying high. So see, in this case, I'm comparing copper 2+ with copper +1. I'm comparing copper 2+ with copper +1. So obviously +2. Tell me one thing. Who will attract more water molecules? +2 or +1? Common sense. +2 will attract more water molecules. So here hydration is more. More for what? Copper 2+ as compared to copper +1. Here hydration is more for copper 2+ as compared to copper +1. Here what is the meaning of this? Ki hydration enthalpy is low and not able to compensate the enthalpy of atomization. They are different things. So if they are asking why copper 2+ copper 0 SRP positive, answer is enthalpy of atomization high, hydration less. But if they are asking why copper 2+ more stable than copper +1 in aqueous medium, hydration of copper 2+ is more as compared to copper +1. That is why what is happening? When copper +1 is added in water, it disproportionate into copper 2+ aqueous and copper 0. You are adding copper +1 in water, it becomes copper 2+ and copper 0. This is a very important and most important question for the D block. Okay, next. Okay, done. K2CR7 and KMnO4, you are knowing they are strong oxidizing agents. They are strong oxidizing agent. In this case, I will focus on one reaction which is very important for KMnO4 mainly, if they are giving KMnO4 in acidic medium, this is going to be converted into Mn2 plus. While in alkaline medium, it is going to be converted into MnO2. In this case, what is important? If I minus given to KMnO4 in acidic medium, this is going to become I2. But here it is going to become IO3 minus. These two reactions are very important. KMnO4 acidic medium, I minus become I2, and KMnO4 alkaline medium, I minus become IO3 minus. You can check here. This is very important for KMnO4 chemistry. Check here. When they are taking acidic medium, I minus become I2. I minus become I2 in acidic medium. But when they are taking in acidic medium, you can check acidic medium, I minus become I2. But now check here. When they are taking neutral or friendly alkaline medium, I minus become IO3 minus. I minus become IO3 minus. This is a very important. Okay, next is F block. In F block, I will summarize it quickly. In case of F block, if you are writing radius, it is decreasing from cerium to erbium, and europium has maximum atomic radii. But if you are observing ionic radii, then cerium 3 plus 2, lutetium 3 plus ionic radii regularly decreases. One question they can ask, in lanthanoids, who is having maximum atomic radii? Answer is europium. Maximum atomic radii among lanthanoids is for europium. But they are asking ionic radii, then regular decrease, cerium 3 plus more stable. One more point, out of lanthanoid contraction and actinoid contraction is more. Out of lanthanoid and actinoid contraction is more. And it is common sense. Says if someone is asking why contraction more, answer is very simple. Attraction is more, so contraction is also more. See, if attraction is more, it will contract more, na yaar. So examiner may ask two questions. Out of lanthanoid, actinoid contraction, who is more? Actinoid contraction more. And if they are asking why it is more in actinoid cases, reason is simple. Attraction is more. So this radius trend is very important for the F block. Okay. Configuration part. In case of configuration of lanthanoid, focus on cerium, gadolinium, and lutetium. In these cases, you can find electron present in D. 5d1 here, 5d1 here, and here is 5d1. In these three cases, cerium, gadolinium, and lutetium, number 1, number 7, and number 14. 1, 7, 14. 1, 7, 14. These cases, one electron present in 5d. Other cases, no electron in 5d. So in configuration part, what is important? Number 1, number 7, number 14. Cerium, gadolinium, and lutetium. These cases, one electron present in 5d. If you observe the atomic radii, you can check there. For europium, it is 199, and no one is more than 199, and they're not writing any data for the lutetium. Okay. But when we are observing ionic radii, it is regularly decreasing from cerium 3 plus to lutetium 3 plus. Lanthanum is a D block element. But it is generally studied with the lanthanoids because of more resemblance with the lanthanoids. Then next, for the configuration of actinoids, how to find? Number 1 actinoid. Now we are not highlighting actinium. Actinium is not F block. No, it is a D block element studied with F block. So number 1, number 7, number 7, number 7, and number 14. They are the exceptions. Here we have 1 electron in D, 1 electron in D, 1 electron in D. Same as lanthanoid. 3 more will come here. 3 more will come just after the thorium. Here we have. Okay. So in case of thorium, 1 minute. In case of thorium, thorium configuration is very important. It is a 6d2 7s2. If you want to write the configuration of thorium, it is a radon 7s2 6d2. It is not having any electron in 5f, even though it is F block element. How to find? Atomic number radon 86 plus 4 is equal to 90. So in this case, thorium is a very important with respect to configuration. Why very important? Because its configuration, thorium configuration is radon 6d27s2. No electron in F, even though it is F block element. This is a very important. After thorium, we have three exceptions where we have electron in D, and number 7, where we have electron in D, and number 14. So for actinoid, exceptions are 1, 7, 14, and just after 1, 2, 3, and 4. Here we have one electron in case of thorium, it is dangerous exception. Here I have 2 electrons in D. Other cases I have 1 electron in D. Is it clear now? And other than these cases, all are normal. No electron in D. Okay, this configuration part is done. Next is oxidation state. In case of actinoids, maximum oxidation state observed for neptunium and plutonium. You can memorize like this: 2 planets, Neptune, Pluto, they have highest oxidation state in actinoids, +7. In case of lanthanoids, they have +3 oxidation state. Other than +3, they have +4 and +2 also. +4 is acting as oxidizing agent and +2 is acting as reducing agent. Out of all, cerium 4+ is a very important. You can check cerium 4 to cerium 3+. SRP is positive, means it is able to act as oxidizing agent. And it is a very important analytical reagent. The cerium 4+ is very important for the lanthanoids. Reaction part is very easy. Most common oxidation to lanthanoid is what? +3. So +3 na, so you can write compound in +3, that's it. Okay, treated with halogen, LNX3. In this case, this carbon reaction is very important. In case of reaction with carbon, major product is LnC2. Other carbides are also formed. This is making Ln3C, Ln2C3 and LnC2 type of carbide. Out of them, LnC2 is the main carbide when treated with carbon. Other you can directly write based on the oxidation state +3. Okay, and then application part is very important. Revise application properly. This is a very important. Okay, so F block also done. Next one. Basic nature very easy na. Lanthanum. When you are moving from cerium to lutetium, size is decreasing, so ionization enthalpy increasing. If ionization enthalpy increases, when you are moving from cerium to lutetium, ionization enthalpy increases. Ionization, because size decreasing. Ionization increases, so what will happen? Metallic character will decrease. And if metallic character decreases, obviously basic strength for the hydroxides will decrease. Okay, clear? In periodic table, I will summarize it quickly because time is less. Radius, when you are moving top to bottom, radius will increase. Atomic radii I am explaining. Atomic radius. Top to bottom radius increases. Exception aluminium gallium pair of the boron family. Means in boron family, boron, aluminium, gallium, indium and thallium. This is going to be reverse. Means top to bottom radius increases. Boron, this you have to reverse. Means gallium, aluminium, indium and thallium. Left to right, radius is going to decrease. Because Z effective increases, radius is going to decrease. So radius constant, focus on this. Top to bottom radius increases. Top to bottom radius, this Z effective increases. So Z effect left to right, Z effective increases. Attraction increases na yaar. Attraction increases, the radius is going to decrease. Clear or not? Top to bottom radius increases, exception aluminium gallium pair. Here I have to reverse it. Means I will take gallium before aluminium for the radius purpose. This was the radius. Ionization enthalpy concept: beryllium, boron, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. These elements are written. Beryllium, configuration lithium 2s1, beryllium 2s2, boron 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. What will happen? In this case, fully filled 2s, this and half filled 2p, they become more than the next element. Only next element means lithium, boron, beryllium, carbon, oxygen, nitrogen, fluorine and neon. In similar manner you can write next also, means below lithium you can write sodium, below boron you can write aluminium, below beryllium you can write magnesium, likewise you can write third period elements also. So what is the method for NS enthalpy? First NS enthalpy, elements written 2s2 and 2p3 will dominate over next, means 2s2 become more than 2p1 and 2p3 become more than 2p4. 2s2 become more than 2p1 and 2p3 become more than 2p4. Reason, penetration power of 2s is more, penetration power of 2s is more than 2p. Penetration power of 2s is more than 2p, or penetration power of 2p is, okay, so if I am explaining this part, I can explain by this, penetration power of 2s is more than 2p, simple. Here I can explain 2p3 is half-filled configuration, half-filled electronic configuration. This is clear or not? So if examiner asks why beryllium more than boron, you can say penetration power of 2s is more than 2p. Why nitrogen more than oxygen? You can answer nitrogen has half-filled electronic configuration. This is clear or not? So this is ionization enthalpy. What I said, right elements, beryllium dominate over boron, nitrogen dominate over oxygen. If someone is asking why beryllium more than boron, you have to answer by penetration power. Why nitrogen more than oxygen, you have to answer by half-filled electronic configuration. In case of group, top to bottom, what I can say, top to bottom, size increases, so ionization enthalpy is going to decrease. Here we have abnormality in boron family, ionization enthalpy. Here we have abnormality in boron family and tin lead pair. So boron family, remember this graph, you will get answer. You have to remember this graph, you will get answer. Boron, aluminium, gallium, indium, thallium. So maximum ionization will be boron, then thallium, then gallium, then aluminium, then indium. Carbon family, carbon, silicon, germanium, tin and lead. These two reverse, remaining normal. Top to bottom ionization enthalpy decreases. So these two have to reverse, decrease, and these two have to reverse. Okay. This is for ionization enthalpy. Electron gain enthalpy. It is positive for beryllium, magnesium, nitrogen and noble gases. These are the cases where electron gain enthalpy is positive. Other cases negative. Few are there in D block also, but not in our syllabus. So these cases electron gain enthalpy positive. Now if you want to write electron affinity taint in second period, remember this trick, NB LIC office. Electron affinity in second period, NB LIC office. N means neon, next B means beryllium, then nitrogen, then boron, then lithium, then carbon, then oxygen and then fluorine. One more point, out of fluorine, chlorine, electron affinity of chlorine is more because of, or fluorine is less because of small size of fluorine or because of compact size of fluorine. Likewise, oxygen, sulfur more. Likewise, nitrogen, phosphorus more. Means in case of P block, out of second period and third period, electron affinity of second period is less than third period. This is about the electron affinity. Okay or not? So this periodic table I summarized quickly because in this case, if I go for the question, there will be waste of time. We have to focus on those relevant concepts which they are asking in main exam. We have to focus on those concepts. Okay, so this periodic table part is also done. I simply said for radius you have to focus on, for radius you have to focus on, one minute, aluminium, gallium. For ionization enthalpy, I said beryllium more than boron, nitrogen more than oxygen in a period. Okay. Chemical bonding, where it is chemical bonding. Okay, in chemical bonding, what they're asking, write the Lewis dot structure of carbon monoxide molecule. Carbon monoxide, this is the structure of carbon monoxide. If I convert this coordinate bond into single bond, how I into covalent bond? This is coordinate, na? If I convert coordinate into covalent, then donor become plus, etc. become minus. After that, you can easily write Lewis dot structure. How to write? By carbon, how many electrons in the valence shell? Carbon 4 electrons in the valence shell, but this is carbon minus, so 5. Out of 5, 3 are bonded here and 2 are not bonded. How to write an oxygen plus? Oxygen, how many electrons in the valence shell? 6. But it is oxygen plus, so 5. Out of 5, 3 are bonded and 2 are not bonded. So if I ignore this part, this becomes Lewis dot structure. Means carbon, these 2, these 3, and this oxygen, and these 2. This is Lewis dot structure. If you want to represent octet for carbon and for oxygen, you can represent like this. So how to write Lewis dot structure? It is clear. Write covalent bonding and put the electrons accordingly. Non-bonded electrons also must be represented in Lewis dot structure. This is simplest way to write the Lewis dot structure. Next problem. Explain the structure of carbonate ion in terms of the resonance. Carbonate ion, C double bond O, O minus. You can clearly observe this minus is going for the resonance. Because of resonance, we may write 3 Rs, one for this minus resonance, another for this minus resonance. So we can write 3 Rs. These are the 3 different Rs of carbonate ion. These 3 are identical, or you can say equivalent. So if I write its resonance, hybrid, or real structure, this is carbon. If I write real structure, oxygen, partial double bond, total charge minus 2, distributed on 3 oxygen atoms, so minus 2 by 3, minus 2 by 3, minus 2 by 3. What is the bond order there? Bond order, total bonds 1, 2, 3, 4. 4 bonds on 3 places, 4 by 3. Means in carbonate ion, all carbon oxygen bonds are equal and they are between double bond and single bond. By 4.3 means what? 1.33 between double bond and single bond. Examiner may ask, in carbonate ion what we have? First option, 2 single bonds, 1 double bond. Second option, all bonds are identical, they are between double and single bond. Answer is all carbon oxygen bonds are equal and they are in between double bond and single bond. If they are asking for carbon dioxide, we have 3 renewable structures, 3 Rs. Like this lone pair going for delocalization, by this you will get this Rs, and opposite case, opposite delocalization means this lone pair coming here and like this, then you can get this one. So examiner may ask, in carbon dioxide molecule, how many Rs possible or how many Lewis dot structures possible? Answer is 3. And what is the bond length of carbon Oxygen in carbon dioxide, answer between carbon oxygen double bond and triple bond. So carbon dioxide we have 3 RS and carbon oxygen bond length is in Hello, now is it okay? Now is it okay? Now, hello. Now, yes, okay. Now, molecular orbital theory, I will tell you simple method by which you can find all possible questions what the examiner is asking. 14 electrons bond order 3. Going this side, decrease by 0.5. Let's say 15 electrons are there, bond order 2.5. 16 electrons, bond order 2. 17 electrons, bond order 1.5. 18 electrons, bond order 1. 19 electrons, bond order 0.5. And 20 electrons, bond order 0. And if bond order 0, then molecule will not exist. Come to this side. 13 electrons, decrease by 0.5, 2.5. 12 electrons, 2. 11 electrons, 1.5. 10 electrons, 1. In this way you can find bond order. So you are knowing for 14 electrons bond order is 3. Going this side decrease by 0.5. Going this side also decrease by 0.5. From this you can easily find the bond order. And if bond order is more, stability is more. Stability is more. Bond order is more, stability is more. Based on this you can find stability concept also. Okay, so in molecular orbital theory, if they are asking any question of stability, number of bonds between two atoms, you can find by this. Two important examples: boron bond, single bond and pi bond. Carbon bond, double bond, and both bonds are pi bond. These two important examples are there. Boron bond, single bond, and it is a pi bond. Carbon bond, double bond, it is also pi bond. Both bonds are pi in these two cases. Is it clear or not? So this is very important concept for molecular orbital theory. Okay, and in case of boron, it is two pi bond only. Carbon also pi bond only. Is it clear? Other than this, if it is given Li2, Be2, B2, C2, N2, these cases 2s2p mixing is observed. In these cases 2s2p mixing observed. But if it is O2 or F2, in these cases 2s2p mixing is not observed. So they may ask which case 2s2p mixing present and which case 2s2p mixing not present. This type of question may be asked by the examiner. For O2 molecule, you have to know directly key its last molecular orbital pi star has 2 electron, pi star 2px and pi star 2py. They are having 1 electron. Because of this, O2 is a paramagnetic. And other than this, you can solve easily. Let's say they are saying O2 plus means remove 1 electron left. It is still paramagnetic but less paramagnetic. If they are saying O2 2 plus, both electrons are removed, no unpaired, diamagnetic. O2 minus, 1 electron is coming, 1 unpaired left, paramagnetic but less than O2. And if O2 2 minus given, 2 electrons came, no unpaired electron, it is diamagnetic. So for O2 directly memorize O2 pi star 2px, pi star 2pi, 1 unpaired electron. By knowing this, you can easily solve O2 plus, O2 minus, O2 2 plus and O2 2 minus. Because bond order you can solve by this trick which I said here. And unpaired electron count you can find by this method only if you are knowing O2 has 2 unpaired electrons, 1 in pi star 2px, 1 in pi star 2py. Because if they are saying O2 plus, remove 1 electron, 1 left. O2 2 plus, remove both electrons. O2 minus, add 1 electron. O2 2 minus, add 2 electrons, 1. So you can easily find. This is a very important concept. Key. If you are knowing about only this small information, O2, you can easily solve O2 plus, O2 minus, O2 2 plus and O2 2 minus. Okay. So last is a test of functional group. Test of functional groups. So test of unsaturation means presence of carbon-carbon double bond or carbon-carbon triple bond. This is done by bromine Br2CCl4 or bromine water test and Bayer's reagent test. Bayer's reagent test. Bayer's reagent is cold dilute alkaline KMnO4. This is actually 1% cold dilute alkaline KMnO4 and alkaline medium provided by Na2CO3 and Na2 CO3, this is also 1%. So test of unsaturation is given, is confirmed by, if both tests are positive, then test of unsaturation is confirmed. Bromine Br2CCl4 or bromine water and bears a test. If both are positive, then test of unsaturation is confirmed. This is for the test of unsaturation. Next one, test of alcohols. For alcohols, we have steric ammonium nitrate test. Steric ammonium nitrate test. And this is performed with a small quantity of steric ammonium nitrate. So test of alcohol, this. Other than this, distinction between primary, secondary and tertiary alcohols can be done by Lucas reagent test. Lucas reagent test. Lucas reagent is what? HCl, ZnCl2. Iodoform test can also be used for some cases to distinguish between primary, secondary and tertiary alcohols. So alcohol steric ammonium nitrate test is used, and 1 degree 2 degree alcohols can be distinguished by Lucas reagent test. Insoluble alcohols are not giving Lucas test. Insoluble alcohols are not giving Lucas test. Next, test of phenols. For phenols, we are using neutral FeCl3 test and phthalate dye test. Okay na? Neutral FeCl3 test and phthalate dye test. Neutral FeCl3 test, for example, phenol reacts with FeCl3. And neutral FeCl3 is actually alkaline. This is going to make FePHO6, and it is Fe3 plus O3 minus this complex. It is imparting violet color. This neutral FeCl3 test is for the phenols, but few phenols are not giving this test. Who is not giving 1 naphthol and 2 naphthols? They are phenols. But they are not giving neutral FeCl3 test. Phthalate dye test is also used for the phenols, but metacresol, this is one phenol who is not giving phthalate dye test. Almost all phenols are giving this test. This paracresol is not giving phthalate dye test. Test of phenols. Carboxylic acid test. Carboxylic acid, when they are treated with sodium bicarbonate, Na plus HCO3 minus CO minus H plus, what will happen? This is going to become RCO minus Na plus plus H2CO3, which decompose and produces carbon dioxide gas, which is giving effervescence. But few compounds are also giving positive bicarbonate test. They are picric acid and 2,4-dinitrophenols. Other than this, if this carboxylic acid is treated with alcohol in the presence of dehydrating agent like concentrated sulfuric acid, this is giving ester, and this ester has fruity smell, fruit-like smell. So for carboxylic acid, we have sodium bicarbonate test, or when we are treating with the alcohol in the presence of dehydrating agent, this is making esters, and esters have fruity smell, good smell. Okay, this is for the test of carboxylic acid. And last, for amines, aliphatic or aromatic amine, aliphatic or aromatic primary amine is tested by CaCl3KOH carbyl amine reaction. It is producing R or PHNC, which is having foul smell or obnoxious smell. So primary or primary amine, any primary amine, aliphatic as well as aromatic aliphatic as well as aromatic, can be tested by the carbyl amine test giving NC isocyanide or carbyl amine which is having foul smell or obnoxious smell, and this RNH2 or PHNH2 is dissolved in aqueous HCl solution. Why? It become pH or R NH3 plus Cl minus, which is soluble in water. So amines can be dissolved in acidic solution. Is it clear or not? And how to distinguish between aliphatic primary amine and aromatic primary amine? Aliphatic primary amine is treated with HNO2, not giving diazonium, giving alcohol. And this is giving, when treated with HNO2, it is giving diazonium. And this diazonium salt is treated with beta-naphthol, giving azo dye or red dye. So we can say aliphatic primary and aromatic primary can be distinguished by azo dye test. Azo dye test positive means aromatic primary amine, and azo dye test negative means aliphatic primary amine. Firstly, go for carbyl amine. Carbyl amine positive means primary amine. Carbyl amine positive means primary amine. Which primary amine? Anyone, aliphatic or aromatic. Then go for azo dye test. If azo dye test positive means aromatic primary amine, azo dye test negative means aliphatic primary amine. And distinction of primary, secondary and tertiary amine is done by distinction between primary, secondary and tertiary amine is done by Hinsberg's reagent. Okay, so this is done. This second inning of chemistry is done. So please focus on the concepts which we discussed, which I explained today, because if you concise all those concepts which I explained by both chemistry faculty, means me and Pansar, then I can assure nearly 120-130 marks are covered. 120-130 marks are covered in both innings of chemistry. Okay, so now I will not take much time. It is already okay 1:30. So take care. Bye bye. All the best, and please revise all the concepts which are explained today to you. Okay, chalo, bye bye, take care.